Hello and welcome to today's event, Azure Quantum Developer Workshop 2. Your feedback is important. Please take a few minutes to complete a short survey that will appear as an announcement at the end of the broadcast. Thank you in advance for your support. If you experience any technical difficulties, please first refresh your browser. If this does not resolve the issue, please send in a message and we will be happy to assist. And now I'd like to turn things over to Mike Bluen. Mike, you have the floor.
Thanks, Jen. Hi, everyone. As she said, I'm Mike Bluen. I'm a Senior Program Manager for Azure Quantum. And today I'm thrilled to have you here with us to celebrate our second Azure Quantum Developer Workshop and the public preview of Azure Quantum. With the announcement yesterday of the public preview, I believe that we're at an important milestone for the industry as quantum hardware and solutions become increasingly accessible to every person and organization on the planet. Personally, I joined Microsoft in 2013, the day after I joined the Azure Data Center Management team, the organization was celebrating a big release for Azure. They had just brought virtual machines to the platform as a service. At the time, this represented a huge milestone for the team, for our company, and for our customers to be able to use the tools that they already knew and loved in Azure at unprecedented scale and ease. Today, I can't help but look back and see the similarities between then and our public release of Azure Quantum. For the first time, we're bringing access to real quantum hardware and scaled quantum-inspired optimization to everybody in the Azure cloud. And not only that, but I'm pleased to be able to give back to the amazing community that is gathered around Q# and the QDK, and around the over 20 years of investment that Microsoft has into Azure Quantum. So it's truly an exciting moment, and I'm very happy to have you here today to share in that excitement. So let's take a look at our schedule for the workshop today. Now to start, my colleague Fabrice will be kicking off by taking you through an overview of Azure Quantum. Following that, we'll have sessions from 1QBit, Honeywell, IONQ, and our own Microsoft Quantum-inspired optimizations, taking us deep on how their solutions work and how you can use them. All the while, we'll be watching the Q&A of the live event, gathering questions to be answered at the end of the event in our live experts panel, where you'll get the chance to get answers on your burning questions straight from the source. So do be sure to post your questions in the Q&A, and some will even get answered during our live sessions. So with that, I'd like to hand it over to you, Fabrice, to help give us an overview of Azure Quantum. Welcome.
Thank you, Mike. And I want as well to thank each of you for joining us today. As Mike said, it is a special moment for the Microsoft Quantum team, and we're thrilled to have you. I also want to thank our partners for joining us today. They represent an integral part of this community and its success. My name is Fabrice Rachon. I'm the lead program manager for Azure Quantum. I'm calling from my home here in Redmond. I've been living in the US for the past 20 years and working for Microsoft for the past 15. Really, most of my career has been focused on building services and operating systems. And my personal experience talks actually quite a bit about what is our mission and why we're building Azure Quantum. We really want to offer a product that is designed to bring you solutions, and that does not require you to become a quantum physicist or mathematician. All what you should have to bring is your subject matter expertise for your domain. I'm going to share a broad overview of the service we just launched in public preview, give you a sense of what it can bring for you and how this new Azure offering is really unique in its nature. First, I want to place Azure Quantum in the context of the efforts that Microsoft has been driving for more than 20 years in the quantum space with the community. We deeply understand the gigantic level of research, industrial and system development it takes to develop a full quantum stack. We understand it because we're directly involved in the development of fundamental building blocks with our own topological quantum computer, and In Microsoft DNA, we're rooted in building platforms that create thriving ecosystems. And so everything we have done in building Azure Quantum is both informed by our first-hand experience in building a quantum system and our deep commitment to have every member of this community to be successful, to recognize the unique value that you bring. The easiest way to think about Azure Quantum is as a marketplace. It is a marketplace that connects quantum providers, the innovator community, researchers, students, system integrators, you really, a vast library of resources that both Microsoft and the community contributes to, and all the customers who can access in a centralized way the latest innovation in the quantum field. As part of building this Azure Quantum platform, it was critical for us to offer a unified development interface. As a developer, it means faster development because you can reuse your code across systems and protect your investments, especially during this current phase of rapid hardware innovation. We're very lucky and very, very appreciative to have this unique group of companies. For gate-based quantum computing, IONQ and Honeywell are offering today their solutions, and a little bit later this year, QCI will join this group. For optimization-centric payloads, alongside Microsoft QIO, OneQubit will show you today some of the fantastic work they have done, and Toshiba will light up soon in Azure Quantum as well. Obviously, our efforts to build this community of quantum providers is just at its beginning, and we're looking forward to share with you the expansion of our group of partners. As a developer, you are at the center of this community, and we value deeply the innovation you bring. We want to accelerate that innovation, and we're committed to give back. That's why we made the decision from the beginning to open source our quantum development language, Q#, the compiler, and the quantum intermediate representation. Our mission with Azure Quantum lies in these connections that we create. We believe we're stronger together. We believe innovation and breakthroughs are accomplished through this tight network. As we're talking about community, we're proud to have a vast network of partners who collaborate with, and that as well you may be able to engage with directly for your own needs. Today, our Microsoft Quantum Network spans hardware and software solution providers, customers and universities, and really represents a comprehensive engine of innovation. Now, I want to take a second to highlight the work done by CQC. Cambridge Quantum Computing is an MQN partner that, among other things, builds a cross-platform quantum SDK called TCAT. And this toolchain allows developers to express quantum algorithms for various devices and is designed to maximize the performance of quantum algorithms when executing on quantum computing hardware, while also doing cool things like accounting for noise and layout difficulties that make quantum programming difficult. We're announcing this week the newly added support of Azure Quantum to the TCAT SDK. To support the growth of this developer community, it is critical we collectively build a common library of resources. With our SDK that is called the Quantum Development Kit, we're really aiming to reduce the time it takes for you to develop. For instance, once you created a representation of your optimization problem, you'll be able to reuse it for all the solvers, both Microsoft ones and our partners, without making any change. You can actually decide to run the same problem against solvers running on CPUs, FPGAs, or GPUs without making any change. And honestly, it's worth pausing for a second. If any of you have tried to convert your code to take advantage of GPUs or FPGAs, it's not exactly a walk in the park. I encourage you to listen to Mark Rusinovich's talk from our September Ignite event. He talks about what we have done on FPGAs, and it's really fantastic. This is the same concept that we apply for quantum computing. This is the whole notion of writing your code once and running and comparing it on multiple targets. You don't have to write a circuit that is highly dependent on the quantum system you're using. We're taking care of abstracting the hardware specificities. When I look at what others are doing, it looks like when I was writing assembly code more than 30 years ago, just trying to extract a few seconds of computation. It was painful and not making me focus on what I was trying to build. We will not have a software industry as we know it today if we're still writing assembly code and focusing on the layout of processors. And finally, Q# makes your code and your skills really future-proof. You can have the assurance that as new capabilities light up in quantum hardware, you'll be able to take advantage of them, and often without even having to make any change. For both of these fields, we have built and continue augmenting development libraries, learning materials, katas, and a rich set of examples to get you started. We're inviting you to contribute, and ourselves, we're committing to provide a continuous curation to ensure the greatest quality of this library. In Azure, and Azure Quantum is no exception, we have a commitment to the security of your data. As you build and scale your solutions with Azure Quantum, you can trust that our entire stack is designed to protect your data and your customers' data. We're also available to support you in tackling your most complex issues, either directly for our Enterprise Acceleration Program or by referring you to some of our system integrators part of the Microsoft Quantum Network. I will wrap by telling you that we're really committed to your success as developers and contributors of this community. Azure Quantum is an ecosystem that opens you the access to the latest quantum innovation, and our aspiration is to unlock solutions today while also preparing you for a future of scale quantum computers. We offer this through an optimization offering composed of both Microsoft and partner solutions, and through a full quantum computing stack that is supporting new hardware capabilities as they light up. I'm very excited to have our partners today sharing with you their latest innovations that you can tap into immediately. And on behalf of the entire Microsoft Quantum team, I want to thank you again for joining us today. Mike, back to you.
Thank you so much, Fabrice, for sharing. As you can see, Microsoft has a deep history with quantum computing and our own qubit efforts, but today we'll focus in on our partnerships to help bring quantum computing to the cloud today. So it's really, really exciting. And I also want to thank Cambridge Quantum Computing for partnering with us. That's one of the most exciting things for me as we bring Azure Quantum to public preview is watching what you build with it. So I'm very, very excited to see these new enhancements to our community coming, and I'm looking forward to see what you build. Next up, I have the pleasure of welcoming the first Azure Quantum partner of the day to the virtual stage, OneQubit. Andrew Fersman, CEO and co-founder, along with a number of their technical team members, will be speaking about the OneCloud provider in Azure Quantum, quantum simulation, experimentation, and some quantum chemistry work that they've done leveraging the platform. Now, before we get into that, I did want to remind you that you can use the Q&A feature of the live event to ask questions during all of our sessions today. Some questions will be answered during the talks, and we'll also be having a live Q&A session at the end of the event, where we'll have experts from all of our Azure Quantum partners and Microsoft ready to answer your questions. And with that, I'll hand things over to Andrew.
Hello, my name is Andrew Fersman, and I'm the CEO of OneQubit. It's a real pleasure to be here today with Microsoft, talking about some really exciting developments in the evolution of practical quantum computing. OneQubit's a company focused on advancing computation and what is computable. And of course, one of the most exciting tools in this effort is the quantum computer. Now let's go to the next slide. So today we're going to talk a little bit about one of our tools that we've produced called OneCloud. We're going to touch on quantum simulation and materials innovation and quantum experiments and our Chemist Cloud tool. And we're going to just start off, if you wouldn't mind clicking to the next slide, talking a little bit about what we can do with quantum computers. Well, it's still really early days, but there's a general consensus that quantum computers will be useful for optimization, for simulation, for artificial intelligence and machine learning, for search and for factoring. And right now, we've already seen the emergence of practical applications that are able to harness optimization and simulation capabilities of quantum processors at a small scale. So this is a really exciting time, and we're starting to be able to use these early machines to address optimization and simulation problems already. Let's move to the next slide. We're really happy because Microsoft is such a one-stop shop for the developer tools that we need to power our solutions. Really, from machine learning to optimization to simulation, you can do it all with Azure, and specifically Azure Quantum. OneQubit really loves the Azure Quantum ecosystem, and we've been an active partner and community member. We're really proud to have used Microsoft Azure to host some of our machine learning applications. We've used Azure Quantum specifically to build up our OneCloud optimization platform, and we're really excited to be announcing today and to be showing you a little bit more about some of our chemistry cloud work. So let's go on to the next slide. We're really excited to be able to talk a little bit about this OneCloud optimization platform that's already available in Azure Quantum. And I'd love to encourage anyone who's interested in understanding more about how quantum computers and the devices that are going to be emerging over the next little bit are useful within quantum computing by heading over to Azure Quantum and checking out OneQubit's OneCloud and the OneQubit solvers. And today we're going to talk a little bit about how Azure Quantum helps us build up a cloud-based product that focuses in a different domain, which is chemical simulations. It's an application area that's even closer to the heart of quantum computing and cloud computing. And so I'm going to turn this over to my colleague Armand to take us through a little bit of this process.
Hello, everyone. Thank you so much, Andrew, for the introduction. It's my pleasure to be here with a group of my colleagues to tell you about some of the exciting quantum simulation projects that we have been working on. So as Andrew highlighted, at OneQubit, we have set out to solve intractable problems and enable others to do so. One area we have focused on is accelerating materials innovation through a scalable and accurate simulation of quantum mechanical systems. Now, much of innovation in material science and drug discovery still heavily depends on trial and error experiments in the lab, very similar to this photo. Our goal is to move to this, efficient and economical in silico simulations of those processes. We want to make these kinds of simulations accurate and fast enough so that they can augment or even in some cases substitute some of the existing experimental techniques when it comes to material design. We are very excited about this goal because it accelerates designing better catalysts, discovering new drugs, and inventing the next generation of batteries for electric vehicles, among many other industry applications. Despite that excitement, though, this is not a trivial task. The reason this has not been fully achieved yet is that our existing approaches to computational chemistry are not efficient enough to accurately simulate chemical systems and reactions in a scalable manner. Let me give you an example. We have a deep long-term partnership with Dow, the leader in the chemical industry, and here I am showing an example of a constraint geometry catalyst that is similar in complexity and size to the kind of compounds that a company like Dow is interested in simulating. Now, simulating this system to the highest level of accuracy would be simply out of reach of existing computational chemistry methods. We would need a computer as large as our galaxy probably to store enough information to accurately represent and simulate this molecule or similar molecules. We are working with our partners to change that. And the way we are going about changing this and solving this problem is by leveraging two secular trends in computing. One is the availability of a scalable cloud computing resources. and the other is rapid progress in quantum computing. The good news is that Azure Quantum is offering both of these, and it is actually allowing us to build a platform for developers that take advantage of both of these trends. The key for us to be able to unlock this tremendous computational potential is to break down complex simulations of chemistry into a smaller, independent subproblems and solve those in parallel without sacrificing accuracy. That's why our team has designed and implemented intelligent decomposition or problem decomposition techniques that would achieve exactly that. And I have in this slide illustration of two different types of these decomposition techniques. This enables massively parallel and efficient simulation of quantum chemistry on the cloud. In addition, we are working on designing scalable algorithms that allow us to leverage quantum computers to solve the resulting subproblems more efficiently when quantum computers are more mature. I'm excited to let you know that we are actually offering these techniques as a service. Our product, Chemist Cloud, combine these proprietary decomposition techniques together with the state-of-the-art quantum and classical solvers to achieve unprecedented levels of accuracy and efficiency in quantum simulations, in chemistry simulations on the cloud. Chemist is built on Azure and is powered by Azure Quantum. And our vision is to accelerate material design by offering accurate chemistry as a service through this product. And let me tell you how Azure Quantum allows us to accomplish that vision. So in this slide, I have a high-level diagram of how our end-to-end pipeline operates. And you see that on the cloud, we decompose a complex problem into small independent pieces and then solve them in parallel on a sea of classical computing resources. This is what Azure enables for us, that on-demand access to these resources. And then in addition to that, it also provides quantum backends to be able to augment some of these solvers with efficient quantum algorithms that can replace or augment these solvers in future. So enough with the high-level explanation. We have prepared a couple of demos to show how this is exactly achieved on Azure Quantum today. In particular, we have two sets of demos for you. The first set focuses on Azure Quantum to run quantum computing experiment exactly in the framework that I just described. And then the second demo focuses on leveraging our Chemist Cloud product and a sea of classical cloud computing resources on Azure to run a massively parallel simulation of some very complex chemistry problems. But first, let's look at the quantum experiment that we designed with our partners at Dow. In this experiment, using the same pipeline that I described, we demonstrate how using problem decomposition can reduce the quantum resources required to run a high accuracy simulation. As it's shown in this diagram, we can use a quantum computer to calculate the energy of each of these subproblems. And this is exactly what Azure Quantum is providing access to. This experiment marks the largest molecular system ever simulated to this level of accuracy on a quantum computer. And thanks to Azure and Azure Quantum, you can easily run similar experiment yourself. And today we want to show you that how to achieve that in our demo. So without waiting any longer, I wanted to invite two of my brilliant colleagues, Valentin Senicourt and Erika Lloyd, to walk you through this demo and show you how we can achieve these interesting quantum experiments on Azure Quantum today. Valentin, it's all yours.
Thanks for the intro, Armin. Hi, everyone. So we believe that quantum computers show a lot of promise in more efficiently solving quantum chemistry problems than their classical counterparts. In particular, they could be used as compute backends to solve the sub-problems resulting from problem decomposition in Chemist Cloud. Azure Quantum allows us to implement that vision, combining these two secular trends of computing we talked about earlier, cloud computing and quantum computing. It provides us with various quantum backends for experimentation, which can be coupled with classical resources from the Azure cloud. Now, let's zoom in on the typical workflow that we go through while attempting to solve one of these subproblems with what we call a quantum solver. From a data structure describing this subproblem, such as a molecular Hamiltonian, we run an algorithm performing several steps before finally outputting an energy value. Most of these steps currently run on classical hardware. First, we apply a qubit mapping in order to reformulate the problem in terms of qubits. We must then define the quantum circuit or circuits, actually, that are needed to compute the energy of that specific problem. And these steps can be very complex and challenging, especially if we try really hard to make it amenable to current quantum hardware. Azure Quantum comes into play by providing the quantum computational backbone of our application, running all of these quantum circuits on quantum hardware such as Honeywell or IONQs. It requires your circuit to be expressed in the Q# programming language developed by Microsoft, and then allows you to execute this code on various devices and retrieve the results. Our application can then finally post-process these results to compute the final output of the algorithm. Today, I would like to demonstrate how Azure Quantum can be integrated to such a workflow by computing the energy of a fragment of a ring of 10 hydrogen atoms with a fixed geometry. In order to do that, we will rely on the DMET problem decomposition and use the VQ algorithm as our quantum solver. If you were to tackle this problem head-on with a problem decomposition, your quantum algorithm would require about 20 qubits. But by applying DMET, decomposing this problem aggressively with a fragment size of 1 atom, the smallest possible, this problem is now reduced to a collection of subproblems, each requiring as little as 2 qubits, depending on the choice of qubit mapping. This reduction in resources is important, considering quantum computers are currently limited in the amount of qubits they can work on, and also, very importantly, the amount of operations they can carry with reasonable accuracy. Back in 2019, we simulated the system for different bond lengths between the hydrogen atoms using the QDK to simulate the quantum circuits. The plot on the right, shown at the Microsoft Build conference that same year, demonstrated that our approach was promising for this system, giving results, the right crosses, that are very close to the full CIF curve in black, which is the exact solution. But now, with the arrival of Azure Quantum, we can finally see how such experiments behave on some of the current quantum hardware. Okay, let's jump right into it. So in this Jupyter notebook, we'll show you how we integrated Azure Quantum to a small Python workflow in order to compute one of the data points in the DMET curve that I've shown you in that previous slide. But this time, we are using an actual quantum processor, not a simulator. That's going to be the quantum processor made by IONQ. We will not run the full DMET VQ algorithm, which is actually an iterative process, but simply the final iteration of that process. Defining the quantum circuits is the responsibility of our application. So for the sake of simplicity, we here decided to use code developed by 1 qubit in order to first quickly generate the quantum circuits needed for that portion of the example, using our own generic data structures, and then translate that information into Q# code. So I'm not writing Q# code, I am generating Q# code as I go. As you can see, 5 files have been written. Indeed, in this example, we need to simulate 5 variants of the same circuit, differing only by the last 2 quantum gates. Here's what our generated Q# code looks like for each of these files. So we see a sequence of Q# instructions, pretty straightforward, that correspond to the different quantum gates of that particular circuit. They have been encapsulated into an operation that is called opYY, and all of that lives inside a given namespace called my namespace. It's pretty transparent. By importing the Q# Python module, these 5 files are then being compiled. Afterwards, the Q# namespace is now visible to our Python application, and the operation it contains can be imported. Here, all 5 of them. We are now ready to submit our experiments to Azure Quantum. We import the qsharp.azure Python package, which exposes several functions related to job submission and management. And using this API, we first connect into our Azure Quantum Workspace. We specify the target device, which is here the IONQ QPU. We then asynchronously submit all 5 jobs with a submit comment, and our jobs are now sitting somewhere in a queue and will be executed sooner or later, hopefully sooner. It really depends on the availability of the hardware you're trying to get a hold on. All right, the next code cell implements a simple waiting loop tasked with retrieving the results of our 5 jobs. The qsharp.azure package makes this pretty straightforward by providing the status and output functions. Upon successful completion, each of the jobs returns a histogram of measurements. You could also just check your job status using the Azure Web Portal under the current Quantum Workspace. It will show you the job ID. You can even download your results separately. I'm sure someone will talk about that later on. Anyway, finally, our application can then post-process these results and compute the final output. The following 1-qubit code computes the energy of a fragment using the raw results obtained in the previous job, but also computes another value using some noise mitigation techniques we implemented on top. We use Azure Quantum to run an experiment on a real quantum processor in the cloud. We see that our application, combined with the IONQ quantum processor, returns results that do not lay too far away from the curve depicting the exact solution and appear promising.
Thanks so much, Valentin, for an exciting demonstration. It's fascinating to see that today you can run such an experiment on an actual quantum computer through Azure Quantum. Another advantage of Azure Quantum is providing a unified programming environment and language for targeting multiple hardware. This is particularly interesting for research and development on different near-term quantum hardware that might have different characteristics or different functionalities. For the remainder of our first demo, I wanted to invite Erica, one of our amazing quantum researchers, to show us how Azure Quantum helps us explore different functionalities on different hardware without having to change our programming paradigm. Erica?
Hello, thanks, Armand. So the previous section shows how critical it is to develop tools that take advantage of a quickly evolving hardware landscape. What we will do now is address some of the realities you might face when running an experiment on current and near-term hardware. In particular, due to finite size, we need to be very resource efficient in terms of qubits. Also, since we are still in the pre-fault tolerant era, we need to compensate for device noise and its induced errors. So in this part of the demo, we will show how Azure allowed us to easily incorporate new hardware features to address both of these issues. So the Azure framework makes it easy to facilitate quantum experiments with complex features. More specifically, we can create circuits with classical and quantum logic using something called mid-circuit measurements. So here we show a circuit where a single qubit is measured in the middle of the computation. This gives us useful intermediate information, and its outcome can be used to classically condition other parts of the circuit. This measured qubit can then be reset and used later in the algorithm, allowing us to be qubit efficient. So this classical quantum object on the left is easily expressed using the qsharp code on the right. So to illustrate the usefulness of such an object, we will show an experiment on the Honeywell device, which has the ability to do mid-circuit measurements and is only available through Azure. So on top, we show a circuit which prepares a quantum state representative of a hydrogen molecule. And what we do is after each gate operation, we entangle the qubits of the original circuit with an ancilla and perform a measurement. Its outcome will indicate whether an error has occurred up to that point. We then reset the ancilla qubit for the next error check. So in this way, we can detect errors at 3 different points in the circuit using only one extra qubit. So running this experiment on the Honeywell device, we saw that for 10,000 circuit runs, an error occurred about 5% of the time. And this is the cumulative error of all 3 of our checks. So now if we post-select the data based on the detected errors, we are actually able to improve our ground state energy estimate. So what we have shown here is how Azure Quantum easily enabled us to run a qubit-efficient error detection circuit by taking advantage of a unique feature of Honeywell's device. And with that, I will hand it back to you, Armand.
Wow, it's wonderful to have a flexible programming language to validate different ideas on different quantum devices. Thank you so much, Erica, for walking us through this experiment. The takeaway is that all of these functionalities are accessible on Azure, where both classical and cutting-edge quantum resources are available. Our product, Chemist Cloud, is also powered by Azure to leverage both of these resources. So last but not least, in our second demo, I want to invite our product lead, Rudy Plesch, who will demonstrate Chemist Cloud to show how Azure has enabled us to build accurate chemistry as a service by running massively parallel simulations on the cloud. Rudy, I'm going to pass it to you.
Hi everyone, I'm Rudy Plesch, the software development lead of the Chemist Cloud platform that we're building at OneQubit. Today I'll use our Chemist Cloud platform to simulate the ground state energy of a molecule with very high accuracy. In Chemist Cloud, we have developed accurate quantum chemistry simulation tools that can scalably and efficiently run on a distributed classical compute cluster on Azure. Chemist Cloud combines problem decomposition methods that break intractably large simulation problems into smaller, tractable subproblems that can be solved in real time. It also uses highly optimized accurate solvers to solve each of these subproblems. Users access Chemist Cloud with a Python client library where they describe the system they want to simulate and the pipeline of decompositions and simulators they want to use. The client library submits the problem to the Chemist Cloud platform where the problem is decomposed into subproblems and distributed on a cluster of classical computing hardware. When the simulation is complete, the resulting energy is returned to the user. The Python API provided in the client library allows users to incorporate Chemist Cloud as a component in their quantum chemistry simulation workflows. Chemist Cloud automatically orchestrates the necessary infrastructure and compute resources that are required to simulate a problem and deliver the results to the user. This eliminates queuing for an HPC cluster. Simulation begins as soon as a problem is submitted. It doesn't matter how fast your quantum chemistry simulation algorithms are if you have to wait a day before they even begin executing. This is powered by the massive computational resources available instantly on Azure. Azure also allows us to deploy a secure environment where many users can simulate their sensitive molecular systems. In the future, it will also allow us to use other types of hardware like quantum computers, as my colleagues have already discussed. But enough talking about what Chemist Cloud does. Let's see it in action. Each user of Chemist Cloud has an account that is linked to their organization. Users interact with their Chemist Cloud account through a web dashboard. Logging in brings users to a log of problems they've submitted. Here we can see a visualization of the molecular systems, the results of the completed problems, details about the solver pipeline, and status of problems that are running. The dashboard is also where users can download the client library, which is the Python package users install on their computers to send problems to the Chemist Cloud platform. Most importantly, the dashboard is where users can get access to their API tokens, which allow them to connect securely to the Chemist Cloud platform. After installing the client library on our computer and configuring the authentication token, we can start running problems. The first thing we need to do is to define what molecule we want to simulate. In this example, we'll simulate ammonia as ground state energy. Here we compose the pipeline of algorithms that Chemist Cloud will use to simulate the system. The pipeline includes a method to decompose the problem into smaller subproblems, algorithms that reduce the complexity of each subproblem, and algorithms to solve each subproblem. When the problem is submitted, it is deployed to the cloud. You can go to the dashboard to monitor what's happening to it, or you can go on to the next problem you want to solve. The problem appears on the dashboard as in progress. The most interesting things here are actually what we didn't see. We didn't have to wait in a queue for hardware. We actually don't even have to worry about what hardware the simulation ran on. For the problem we ran, we needed to solve 31 subproblems. But this is just a toy problem. We've run problems with many orders of magnitude more fragments. The Chemist Cloud platform automatically allocated enough compute nodes of enough power. This is only possible because of the availability of computational power provided by Azure. Efficient communication between the compute nodes and all the code required for parallelism is automatically handled by the Chemist Cloud platform. When a simulation is complete, the resulting ground state energy is returned to the client library. There are many important industry applications where calculating the energy is a step in a broader chemistry problem. The client library API allows you to use Chemist Cloud simulation service seamlessly in whatever chemistry simulation workflow you have. Chemist Cloud is secure, scalable, compatible with future hardware, and powered by Azure. If you'd like to be part of our early access program or learn more about Chemist Cloud, please contact us.
That was fantastic. I get excited every time I look at that demo. Thank you, Rudy, for showing what Chemist Cloud has to offer on Azure. In summary, today, we wanted to share our experience on Azure Quantum with you and to tell you how it has enabled us to derive value for chemistry simulations and in the context of our work with our partners. Particularly, we wanted to show how Azure Quantum has enabled bleeding-edge quantum and quantum-inspired hardware at your fingertips, as well as on-demand cloud resources for deploying powerful, scalable services to solve computationally demanding problems today. And at 1Qubit, we wanted to show how we leveraged Azure and Azure Quantum to build a scalable product, Chemist Cloud, that can push the boundaries of quantum chemistry simulations on the cloud to provide accurate chemistry as a service. Now, with that, I wanted to thank you all for staying with us throughout this presentation and listening to us. Please don't forget to join our alpha user list for Chemist Cloud at the address shown here and similar to one that Rudy showed moments earlier. I also wanted to let you know that a few of my colleagues are going to be available in the live Q&A session that is coming up to answer any questions that you might have. I wanted to mention too that this effort and what we were able to show you today has been a team effort. So I wanted to send a big thank you to all my colleagues and 1Qubit who enabled this. And on their behalf, I wanted to thank you again for your attention and for listening to our presentation.
All right. Thank you very much, Andrew and team. Now, I'm a huge fan of the optimization solutions that you're bringing to Azure. And after just over a year of working closely with the 1Qubit team following the announce of Azure Quantum, I am continuously impressed by the energy and the expertise that the 1Qubit team brings to solving real-world problems with quantum technologies. And I think that OneCloud and Chemist are excellent examples of why we built Azure Quantum. It's to empower you to solve interesting and impactful problems. Azure Quantum and Q# represent the fundamentals, a platform and a language to build on, but there remains a tremendous amount of innovation coming from the community around applying the latest techniques and algorithms to solve difficult problems today. And after we release the preview, this is the thing I am most excited to see, what you build with the service. Now, next up, Brian Ninehouse from Honeywell will be speaking about their quantum systems available today in Azure Quantum and giving an overview how they work and demonstrating some sample algorithms with the Honeywell systems. So with that, I'd like to hand it over to Brian. Thank you very much.
All right, thank you very much for having me today. My name is Brian Ninehouse. I'm the commercial operations leader at Honeywell Quantum Solutions, and I'm excited to talk to you today about how you can use Honeywell Quantum Solutions quantum computers through Azure Quantum. So just a tiny bit about me. I have degrees in physics from BYU as well as the University of Colorado, where I got my PhD, but really cut my teeth into quantum simulation and quantum computing as a postdoc at the University of Maryland. And I just kind of found myself accidentally employable, if you will, right time, right place, getting into quantum mechanics and quantum computing. And hopefully you guys all find yourselves in the same position, right? This is a very exciting time to be not just building quantum computers like I get to do, but also to be using them as well. So today what I want to talk to you about is sort of introduce you to the Honeywell quantum computing system, talk about some of our differentiating features, but then also talk about how you can use it through Azure Quantum. Talk about going all the way from your Q# code down to our machine and back up, and then even top it off with a demo about a repeat until success circuit, which I think is quite interesting. So sort of in my naive physicist brain, how I think of quantum computing is you come up with some circuit. This is generally how I think of quantum circuits, with these lines and boxes. But if you have some other representation you prefer, that's all right. And you code that up into your favorite programming language. In this case, Q#, this nice functional representation where you can write in all these different functions that program the quantum computer using all the tools you know and love in Visual Studio. And then you're going to submit that to our quantum computer. right? And I purposely made the background here black. This could be just a black box to you. Something happens, a miracle occurs, and then out pop results, right? Some histogram of the results from the circuit that you ran. And to be honest, you can run your quantum programs on our machine without knowing a whole lot about that black box. That's completely all right because we have these high-level programming language tools for you to submit your programs and then analyze your results. You don't have to necessarily know about the details of our quantum computer in the same way that I blissfully am ignorant of what happens on my CPU and my laptop when I program in Python or any number of other programming languages. But just because I don't need to know what happens in my CPU to program well, there are people who do. And if you really want to make complicated programs, optimized programs, knowing how your program interfaces with the hardware underneath is actually fairly important if you really want to be able to optimize your program's efficiency and take advantage of all the features that new hardware has to offer. So my goal today is to give you a peek behind this black box, let you know what's actually happening on the hardware as you submit your quantum circuits, with the goal that hopefully it will make you a more efficient programmer. It will make you aware of some of our differentiating features that are not available on all the other quantum computers that are out there. But also it's just a lot of cool. As a physics nerd, I like talking about this stuff. So you get to take a journey with me down to the atoms that make up our quantum computer, and then all the way back up to Q-sharp code. Hopefully, and this will make you a better programmer as you submit jobs to our machine. So at the very base of our quantum computer are our qubits, and these are ytterbium-171 ions. So ytterbium is just a metal. It's an element on the periodic table. It's down in that lanthanide section that always gets pulled out and put below the rest of it. But what it is isn't so important. It's an individual atom, and we rip off one of the electrons. And we do this for two reasons. The first is that once it's ionized, it has a positive charge, and now it's really easy to grab onto and move around. So on the left here, you'll see a picture of one of our traps, and this looks very fancy. There's a lot of complicated technology underlying this, but at the most basic level, it's just a bunch of electrodes that we can apply voltages to hold on to these charged ions and move them around in our trap, right? So I told you earlier that we use a quantum CCD architecture, a quantum charged coupled device architecture. And what this means is that just like charges are shuttled around in the CCD sensor at the back of your digital camera, we shuttle around our ions, which are qubits, around our trap. And this was a phrase coined by researchers at the National Institute of Standards and Technology quite some time ago as a way to build these large-scale quantum computers where you could shuffle your qubits all around and connect them in whatever ways you needed to. Right, so we ionize our qubits so it's easy to grab onto, but also because then that gives us a very useful internal level structure that we can use to manipulate our qubits. So we've picked two of these states in the electronic ground state to be designated as our 0 and our 1 state. Right, so this looks just like classical computing, but remember, because this is an atom, it's a quantum mechanical object, I can actually be in some superposition of 0 and 1 at the same time. And that's where the magic of quantum mechanics comes in. But whether it's a 0 or 1 in this case is really just saying, is the spin of the nucleus and the spin of the electron, are they aligned or anti-aligned? And those are my two states. Right, these states are very long-lived and they're very stable. In fact, these are the same states you would use to make an atomic clock if you chose ytterbium as your atomic clock of interest. So they're very insensitive to external perturbations, which means that we can have very long coherence times and makes it easy for us to be the only ones interacting with our qubits, have no accidental interactions with the environment that could destroy our quantum information. Right, we also have barium ions there in our trap too. They're not so important. It's just another element on the periodic table. And they're around so we can cool our qubits as we do a computation. But they're not actually quantum mechanical in the sense that they are not qubits. They're just along for the ride. We're going to ignore them for the rest of this presentation. So these atoms are loaded into our trap and they're shuffled around, levitated above the surface of this trap, and that's the heart of our quantum computer. That sits inside a vacuum chamber. So it's a big stainless steel bowl about the size of my head that isolates these qubits from the rest of the environment. We've sucked out all the air, so air molecules don't smash into them and destroy their quantum states. And we've actually cooled the whole thing down to about 20 degrees Kelvin to further isolate them from their environment by creating even better vacuum. Now, this isn't as cold as those really cool looking chandeliers you see with the superconducting qubits. They're all the way down at millikelvin. We only need to go down to about 20 Kelvin or so for our purposes of reducing vacuum pressure. Right, so we have our qubits. They're in the center of this vacuum chamber, and its job is to make it so nothing interacts with it, except for the signals we apply. So the rest of this gigantic lab is focused on making the signals that go to the trap to shuffle these qubits around, and then making the right laser pulses going through all these optics, and then shining in on our qubits to mediate the interactions between them and run our quantum circuit. And then, of course, there's one last piece, which is at the end of a circuit, or in the middle of a circuit even, when we want to measure what state a qubit is in, we shine a laser beam on, we collect the fluorescence, the light scattered off of that qubit, and we collect that on these measurement optics below, so we can actually get some information out of the quantum circuit at the end. So what does that look like for a circuit, right? So here on the left, I've got another quantum circuit diagram. This is different than the one I showed at the beginning. The one I showed at the beginning is a very interesting circuit called repeat until success. This one is a complete nonsense circuit that does nothing interesting at all, but it has all the same elements to it, and it was a lot easier to do the animations for this, to walk you through how just a generalized circuit would work on a quantum computer. And on the right here, I've got sort of a zoom in of a portion of the trap, and you'll see that there's all these different boxes. The two long lines are our electrodes where we apply radio frequency voltages to, and that traps the qubits along that line. And then all the little rectangles are our DC electrodes that we use to shuttle the qubits back and forth and put them in the right locations. So you'll see the darker squares are our interaction zones. That's where our laser beams live. And the lighter squares are our auxiliary zones, where we can sort of store qubits when they're not needed in one of these interaction zones. So to be concrete, let's just load the trap with 3 qubits. Here I've labeled them red, green, and blue. Of course, in actuality, all ytterbium ions are exactly the same. You can't tell them apart, which is good. That's what allows our quantum computer to work. But for this example, this will make it easier to track. So the first thing I want to do is apply a set of laser pulses and initialize these qubits to some initial state. In this case, it's the 0 state. So I can shine those lasers in on all 3 of them and initialize them. The next step, time step 1 here, I want to apply some single qubit gates to the red qubit and the green qubit. Now, luckily, they're already in the right location to do this. So again, it's just shining on another laser beam with the right parameters to do a single qubit gate. And it's the same laser beams, whether I want to do a Hadamard gate shown here or some other single qubit rotation. We're just adjusting parameters of that laser beam, slightly different phases and whatnot, to do different single qubit gates. But they always take place in those interaction zones there. But if we look ahead to time step 2 now, things get a little more complicated, because I want to do a 2 qubit gate, a C0 gate in this example, between the red and the green qubit. And to do that, those 2 qubits have to be right next to each other so they can interact. So before we get to time step 2, we'll reshuffle our ion chain here, and we'll move the green ion over to the red and then join them together in a single well. So now they're sitting about a micron apart. And once they're in the proper location, we can then apply another pair of laser beams in this case to do this 2 qubit gate interaction. Okay, looking ahead to time step 3, another 2 qubit gate, but this time between the red ion and the blue ion. And so what we need to do here is a bit more complicated. I need to swap the position of red and green, move red over to blue, and then join those together. But although there was lots of steps there, really, again, this is just a series of voltages applied to these electrodes to move these qubits around. This is all classical control. So there's always a shuffle our ions around to be in the right spot step, and then a shine the laser beams on to do our interaction step here. And then time step 4 is the last one I'll animate here. It shows we want to measure the green qubit here. And so I'll shine the laser beam onto that green one. Luckily, it was already isolated from everybody else, so I it without disturbing the red and the blue qubits, which are in the machine here, right? And this is an important feature. I'll come back to this. The ability to move our qubits around means we can isolate them from the others when we do these interactions. It means we can measure or reinitialize a qubit without disturbing the quantum information stored in the other qubits in the machine. So although I ran out of space for my animations here, I could then reinitialize this green qubit and continue to run things, run future gates in the circuit after this measurement, and even have those conditioned upon the measurement value that I just got out of that green qubit there. So an actual sort of physical space, here's what this looks like. I've got split combine going on the top, where you'll see these little white dots moving around. Those are individual ytterbium ions you're seeing. You're actually seeing the fluorescence that's been then captured on a CCD camera below. And we can move them from 150 microns apart to the same zone, so they're right next to each other, and then move them so they're so close together it just looks like one dot there. That's sort of splitting and combining these ion chains. And below is an animation, again, real pictures of real ions of our swap, where we have two qubits right next to each other, close enough it's kind of hard to make out that there's even two ions there, and we rotate them around each other. Now, when this actually happens in our device, we're not shining our lasers on, so this happens in the dark, which is good. You don't want your qubits to interact with the lasers except when you're trying to do an interaction. But for this animation, so you can see it happen, this is kind of neat to see these individual atoms going through this dance there. Okay, and this ability to shuffle our qubits around in this QCCD architecture has a lot of advantages. The first I'll say is that it natively gives us all-to-all connectivity. It doesn't matter which of our qubits in the trap you want to interact with each other. We just move them next to each other into an interaction zone, and then apply our lasers, and away we go. There's no cost for doing an ion on one side of the chain, interacting it with a qubit on the other side of the chain, because we can just move them right next to each other. And any pair is equally good. As compared to other architectures where perhaps you have a fixed number of qubits and a fixed orientation. And if you want to get your information across, say from the top left to the bottom right there, there's going to be a series of very costly logical swaps that have to take place to do that interaction. I think this is also very nice for you guys as programmers of quantum computers, is that you don't have to worry about what the physical layout of the chip is because it's completely reconfigurable. There is no optimal pair of qubits to be run. All pairs are equally good. So you can just program the circuit you want and not have to worry about that layout there. I'd say another great advantage of this QCCD architecture is that you sort of natively have these very high fidelity gates. When we do, well, any of our interactions, the qubits that are interacting with our lasers are isolated from all the others. We move them many hundreds of microns away. And so we just have to worry about the qubits that we're targeting. So for a 2-qubit gate, that means when we do a 2-qubit gate, it's just the 2 qubits we care about in that single well, and everybody else is way out of the way. And so it's a very clean, pristine interaction that we can control very well and get high fidelities. It also means that as we add more and more qubits to our trap, our fidelities will stay the same because it's that same basic interaction, right? 2 qubits in a single well, and the fact that there's more sitting way out in the wings, well, doesn't matter. They're far enough away that they don't influence that interaction, right? And so some of our fidelities are listed below. We're sort of limited by this 2-qubit gate fidelity, which is a little better than 99.5%. Single qubit gate is an order of magnitude better there. And our state preparation, measurement crosstalk, again, these are all very good because when we measure a qubit or prepare a qubit, we can move everything else away. And the last feature I'll point out, which is sort of unique because of this QCC architecture, is that we can measure a qubit and reuse it without destroying the quantum information in the rest of the chain, right? So this is very useful in what we'll call the NISQ era, this noisy intermediate scale quantum computing era, where the number of qubits you have is limited because you can use the same ancilla qubits over and over and over again. So you can run programs on our machine you can't run on others because you can reuse these ancilla qubits as you want. You can finish it, keep running the circuit. But I'd say the more exciting thing for me anyway is that you can do conditional logic. You can measure some subset of your qubits and then make a decision based on that measurement, which influences the rest of the circuit you run. And this is exactly what we need to do for quantum error correction. If you're going to have any large-scale quantum error correction, you're going to need to be able to probe what's going on in your system in the middle and then apply corrections as you go. And so mid-circuit measurement and qubit reuse is absolutely essential for this. This is something that everyone will have to invent eventually to progress in quantum computing, but it's something that comes quite naturally because we can easily reconfigure our qubits in this QCCD architecture. So back to this original story, I have a circuit that comes from my brain. We code it up in Q#. We submit it to this black box where ions are shuttling around and laser beams are firing at them, and we get results. I feel like I maybe need to connect this a little bit more. How do we go from Q# code down to these ions being shuffled around? Well, Q#'s a great language. It allows you to program very complicated circuits quite elegantly using all the tools you know and love from Visual Studio. But we need something a little different to run on our quantum computer. So actually on the Azure cloud, it compiles this down into some quantum assembly language. And this intermediate representation gives us a time-ordered step of all the things that need to happen in our computer. So I go from these beautiful if statements and functions that are being called to a list of do this gate, then do that gate, then do this 2-qubit gate, then do this measurement. And you can see there's still if statements in there, but again, they're all serialized now in time. And this is closer to what I need to actually execute it on my quantum hardware, right? That's still not quite what I need. We've now specified which gates happen on which qubits and in what order, but we need to know a little bit more, and that's where these qubits should be. So our compiler on our system takes this CHASM code and it compiles it down into control system instructions. So now if you squint really hard and look at the tiny print here, you can see there's commands like shift and split and combine. These are all these ion shuffling commands that move the qubits into the right location. And then after those, we have things like IONQ, which is a single qubit gate, or ZZ, which is our 2-qubit gate, right? So now we're not just serialized which gates happen in which order, but all the way down to this ion shuffle dance that goes on and the actual pulses that are applied to our circuit. And this set of control system instructions is then given to our control electronics, which then use that to apply different voltages to our trap to shuffle our qubits around and then turn on and off these laser pulses and change their frequencies in the right ways so we can apply these gates. Also in this set of control system instructions, you'll notice the word measure popping up there every once in a while. And when we do a measurement, again, it's just another laser beam shining on one of these qubits, and we'll catch that fluorescence from the qubit with these measurement optics. And we can read out a strings of zeros and ones, which are the results of that measurement. If the qubit is in the 1 state, it scatters lots of photons, that's a 1. If the qubit's in the 0, it scatters none, and we record that. And so in this case, there was just 3 measurements. So you'll see that each run of the experiment, or each trial, you get 3 numbers, 3 bits, 0 or 1. And then we repeat that, in this case, 100 times to get our dictionary results, which we then flow back to Azure, and you get these nice histograms showing your results, right? So you go from Q# down to some intermediate representation that gives us this time-ordered set of instructions, down to very detailed level of which qubit goes to which location at what time, to get a dictionary of zeros and ones, which is then flowed back to our histogram. And that's how your quantum program is executed on the Honeywell system. So I wanted to show you, I've been teasing this code the entire time with this repeat until success algorithm. That's what the Q# was. That was actually the CHASM code and the compiled hardware instructions for this circuit. So now let me tell you what it is. So this is a really neat quantum circuit that comes from the paper that's shown right below it there. So this is not something I invented, but it's this really neat circuit that allows you to use these 2 control qubits up top to do a rotation on this target qubit, which I've labeled it state psi, in a deterministic way. So you run this gadget, and at the end you measure these 2 auxiliary qubits, and if they both measure 0, then you rotated the state psi to this new state. And it's kind of a goofy form there. That's an odd rotation to choose, I suppose. And the exact specifics of it aren't so important. But what's really neat is that if you measure something other than zeros on both of those auxiliary qubits, the state psi remains unchanged. So I can rotate this state and know that I was successful because of the measured outcomes on these auxiliary bits. But if I wasn't, I haven't messed up that state psi. Right? Now, it's just a 3-qubit example. You may think this sounds sort of silly, but this has a lot of really good applications when you start dealing with logical qubits and you start trying to make magic states. Now, if that doesn't mean anything to you, that's fine. But this gadget here is going to be a very important building block in building some very nice quantum codes in the future. I'll zoom in and show you it's actually even a little cooler than that. Is that this first chunk of the code that I've highlighted in green here is a repeat until success algorithm all on its own. I can take these 2 auxiliary qubits, entangle them together, measure just the first one, and already I know if I succeeded in creating this resource state, which allows me to rotate that state psi. So I can create this as a resource ahead of time and know that my auxiliary qubits are the right state before they've ever touched my state psi, and save sort of these complicated interactions there. Right, so what does this actually look like when I run this on the machine? Well, I run this gadget, I have my 3 qubits, I initialize them to some states, I run the series of gates, I measure my 2 auxiliary qubits, and if they both measure 0, I'm done, I succeeded, I rotated my state. But if they don't, well, I just reinitialize those 2 auxiliary qubits, leave the target qubit psi completely alone, don't touch it at all, and run the gadget again, right? And now I can check again, did I succeed this time? If I measure 0 on both these measurements on the auxiliary qubits, I'm done. But if not, I can run it again, and I can keep going until I finally get the measurement that I want. So we ran this on Honeywell system model H0, which is a 6-qubit machine. You can see this example only used 3 qubits, so the other 3 were sitting off board to the side, I suppose. But this is the results we got. So on the y-axis, we have the success probability, and on the x-axis, you have the number of iterations we allowed the circuit to run. So if you only allow this repeat until success gadget to run once, well, you succeed or you don't, and that's the end of it. Now, the dark blue line, which is slightly higher, that's the simulated value, the simulated results. This is what you would expect if you had a perfect quantum computer with absolutely no noise. And the lighter blue line below it is the results from Honeywell system model H0. So you can see if you just run it once, there's about a 70% chance that you're going to get the right answer, and that's the end of the story. But now if you allow it to run twice, so there's a second chance for you to get it right, that probability of success goes up. And a third time it goes up, a fourth time it goes up even more. And in the perfect computer, it would slowly asymptote to 1. But you can run this as many times as you want because you will know when it succeeds. So this was really exciting for me to see. This is the first time I think a repeat until success circuit has been run on any quantum hardware to my knowledge, because you need this ability to make measurements in the middle of the circuit and then do something as a result. These quantum if statements. I can't imagine writing a program without an if statement, and so I can't imagine programming a quantum computer without an if statement. And you need this mid-circuit measurement to do that. So we'd really like you to program on our quantum computer. So what's available to you on Azure Quantum? Well, there's Honeywell system model H0. That's the machine I was just talking about. It's been available to our external partners for a little over a year now. It has 6 physical qubits and a limiting 2-qubit gate fidelity of 99.3%. And that has a measured quantum volume of 64, which I will point out is the largest quantum volume of any computer out there until we release system model H1. That was released in November of 2020, so much more recently. It has 10 qubits, slightly higher 2-qubit gate fidelity, and as a result, we measured a larger quantum volume on that system. Now, I should point out that these are current specifications. That's the performance of the machine today. We are continually upgrading these machines. So I fully expect the system model H1 to increase both in qubit number and in fidelity over the next year. We've got a whole string of upgrades which we're planning to apply to the machine, so we can continue to get better and better performance from it. Now, in addition to these two systems that exist, we're of course looking even further into the future. So I won't give numbers or dates for any of these, but here's what's in our future as far as the other machines we hope to be releasing over the next 10 years or so. So system model H0 and H1 are actually both the same linear trap. We already have model H2 sitting on the table in our lab. It's this racetrack, which allows us to put more qubits into the system. And we're working on a lot of the development pieces that go beyond that as well. We have junction traps. We've demonstrated the ability to move qubits through a junction, which is what you'll need to do a full two-dimensional tiling of qubits. We've been focusing on the development of integrated optics and these sort of large-scale strategies to get to more and more qubit numbers, all while keeping the fidelity high. So we're very excited for you to help us with our development here. I think the quantum computers right now are still very much in their early days, and we'd love to see what inventive things can be run on it. So we're very excited for you to use our quantum computers through Azure Quantum, and thank you very much for your time.
Thanks so much, Brian, for walking us through how your system works and how everyone here today can use it on Azure. It was really interesting watching how Q# programs are compiled for your system through quantum assembly and machine language, and all the way down to the actual shuffling of the atoms. This is one of the most powerful features of Azure Quantum and Honeywell's integration with Azure Quantum. You can write high-level quantum programs in Q# while leveraging the classical control and the set of libraries made available to the community. And as the programmer, you don't have to worry about how all of that actually gets implemented in hardware. And I particularly loved the graphics that you showed of the dancing ions actually implementing the quantum operations. Now, you called that split and combine, but have you considered the electric slide? All right, I'm gonna have to show myself out after that one. And while I do, we're going to go on a quick 15-minute break so you can refresh your coffee or tea or get a bad joke out of your head. During this time, you'll also see some videos from the Azure Quantum team and hear some of our customer success stories. We'll see you again in 15 minutes at 9:30 PST.
We are really excited to engage with Microsoft on Azure Quantum because we know that quantum provides a path to solve the most complex optimization problems, and that's important to our future.
70% of the goods in the US are moved by trucks today. Trimble is engaged with the transportation industry for many years. We have domain experts from supply chain to routing optimization and fleet utilization. This, together with the sensors data that we get from Trimble equipment, deliver the required information for the solutions that we are developing.
The primary friction is really the movement of data in real time.
Azure Quantum offers a mechanism to do that in a way that we could not do in the past.
We are aiming to a point where the data we collect becomes knowledge and real-time insight.
If that information and that knowledge is available to the shipper, then the shipper can look at alternative carriers or look at alternative shipping plans and meet its objective, maybe a lower rate, lower cost to move the goods, and the carrier gets to increase its utilization.
Not just some destinations we are trying to connect. There are a number of other parameters that come into making an optimal route when we connect a shipper and a carrier. There are hundreds of thousands of connections to be made, and finding the most optimal one is definitely a very hard problem to solve.
Considering the complexity, we envision that quantum technology will play a crucial role in the industry optimization journey.
What's challenged the industry has been the expectations of the consumer. With the pandemic, we've seen the acceleration of e-commerce. It multiplies the complexity of the supply chain. The power that we now have available to us and the data that we have available to us is so much more than what we had before.
One of the things that really gets us excited with Azure Quantum is that it gives us an opportunity to start to engage and bring our domain to talk about these problems and the complexity, and work with a team that is not only building quantum-inspired algorithms, but is actually working to provide a pathway for companies like Trimble to engage in fully enabled quantum optimization.
And we were solving such small problems before with computers. Today, the sky's the limit.
The Microsoft Quantum Program is a global scale program focused on enabling commercial scale quantum computation. It's really about bringing quantum impact to people today and tomorrow.
Quantum computing has the opportunity to make an impact on the world right now in a revolutionary, game-changing way.
We're focused on developing every element of the quantum system, an end-to-end full-stack technology from the algorithms to the software stack to the hardware itself. To reach a commercial scale quantum computer, it requires revolutionary discoveries across physics, computer science, mathematics, materials science,
all of which have to come together to make topological qubits and multi-topological qubit systems. We have a team that's spread across 8 labs around the world. Although we're spread out, we are one team working towards one goal.
Building a quantum computer is a huge task. It's all the way from the software all the way down to where we control the quantum states that makes up the qubits.
Here in the lab, we have fabrication technologies, nanotechnology, that allows us to turn the dumb materials into smart devices.
The Microsoft Quantum program allows us to dream big. We need to dream big.
Azure is the world's computer. You have access to the tools, services, and solutions in a very familiar environment. And with Azure Quantum, we're bringing quantum solutions forward to that environment. We're bringing quantum impact to your fingertips. We're working with enterprises and companies around the world, energy optimization, risk and financial analysis in medical diagnostics, to identify where quantum solutions will bring about impact for their businesses. A great example is Case Western Reserve University.
We're working with Azure Quantum to optimize the way that people get MRI scans. Patients have access to faster and better MRI scans in a way that wasn't possible before.
We can make those scans up to 3 times faster by using quantum solutions on classical hardware today.
The really high-level scientific goal is to be able to solve problems that we can't solve today.
Azure Quantum enables every developer, every person, every enterprise to really tap in and succeed in their businesses and their endeavors with quantum solutions. And that's incredibly powerful.
If you think about MRI today, the problem is that it takes a while to scan. The other problem is that the MRI scans that we do today have limited sensitivity. So we can see some diseases, but there are other diseases that we can't. Our laboratories developed a new way to do MRI scans called magnetic resonance fingerprinting.
In general, we want to make the MR scan faster and more robust, meaning that we can get good result consistently, no matter where the patient is scanned.
Azure Quantum has really inspired us to look at the future. In every fingerprinting scan, there's actually thousands of decisions that we have to make in order to set up the right scan. Surprising, but the scale of that optimization problem is beyond what we can solve with conventional computing.
Conventional optimization algorithms, typically they have some assumptions. For example, they assume that scanner system is perfect or patient in the perfect position. But in reality, there are lots of confounding factors that may change the signal. If the algorithm does not consider all this, then the result may not be optimal.
We're working with Azure Quantum to use their quantum-inspired algorithms to start to solve these problems.
We provide the question and the target, and they're using their algorithm to help us to find the optimal results.
Working with Azure has given us improvement in speed and about a 30% improvement in our precision. The results we're getting are allowing us to see diseases earlier than before and to quantify the treatments that we're giving. Working with Azure Quantum has enabled us to do things that we just couldn't do before. It's really changed the way that we think about MRI scans, and we see a whole new world of possibilities that we didn't before. These results from the quantum-inspired algorithms are going to impact the healthcare of billions of people worldwide.
At Ford Motor Company, Quantum is a new initiative. This is probably defining the future landscape of the entire computing industry. Right now, every car is a moving computer. A huge amount of computations are being performed in vehicle or via the cloud.
Quantum's really promising for how it can solve problems that haven't been traditionally solved before. We are looking at ways now that we can take some of the concepts from quantum and apply them to problems we have today.
In our collaboration with Ford, they bring to us physicists, computer scientists, engineers with years of experience in the automotive industry. And we are bringing mathematics, physics, computer science, algorithms, expertise to forge a solution. It's really a team effort. So in building our techniques for the automotive industry, we rely on quantum-inspired optimization. It is developing new quantum algorithms tailored to their difficult problems and simulating them on today's computers.
With Ford, we are looking at all the possible ways of how quantum can help them.
One of the use cases that we explored in the phase 1 is a congestion mitigation problem, where you have a bunch of cars requesting for routes at the same time and planning to share the same route segment in a city. Under the current technology, there's a selfish routing algorithm that works, where you actually assign routes to each of the vehicles so that they can optimize their travel time without even being worried about how many cars are planning to share the same route segments, which actually creates a congestion.
What we've seen with bringing quantum-inspired optimization to the traffic optimization problem is we can solve these problems, in some cases, multiple orders of magnitude faster than can be done with conventional electronics. And that could really have an impact on people's everyday lives.
We have the vision in terms of what can drive the future of not only the automotive, but also the future of computing.
It's really great to see how ideas that until recently were just used in academic contexts to be applied now and useful for its products.
We're just scratching the surface with looking at traffic optimization. We see opportunities across the spectrum in automotive, everything from traffic, thinking about mobility as a service, to things like design of better materials and new types of batteries. The possibilities really are endless.
The automotive industry is unique in that it's got really high volumes and touches people every day. So even changing small things for the better make huge impacts both in to our business as well as to our customers.
Willis Towers Watson covers actually an amazing range of services. They're all around, though, the issue of people and risk.
One of the things that sets Willis Towers Watson apart is the use of advanced technology to solve client problems.
Engagement with Microsoft started where we wanted to work with them on the idea of quantum computing, preparing for quantum computing by starting off with what we call quantum-inspired computing today. This is a breakthrough that is going to provide incredible computational power and a different way of really computing.
Risk modeling is a little bit different to classic big data AI sort of problem. With risk modeling, you're trying to quantify the whole distribution of outcomes. It requires quite a lot of specialism, and the prevalent technique is something called Monte Carlo simulation. Simply put, we roll the dice lots and lots of times and calculate from the resulting outcomes.
Quantum-inspired optimization leverages the principles of quantum physics to solve optimization problems in a faster to higher accuracy.
Currently, we can run sort of realistic models in 10 or 15 minutes. If we can bring that down to seconds, then immediately that's opening up the door to real business value.
What this means for the end user is we give them information and insights that they were never able to have before. The limits of traditional computing just meant that we couldn't analyze certain things. With greater insights, then comes more efficiency and better choices. I love the quantum-inspired computing, partly because of the problems that we're going to be working through with Microsoft today, but perhaps more because of what we'll do in the future. The problems we're tackling today, we'll get some great insights and some great results from them, but there'll probably be things that we haven't even begun to think about today that'll give us future results. That's what's really exciting.
Hi, hope you're enjoying the workshop so far. Today we're going to tell you a bit about IONQ, how we compute, some of the benefits of our platform, and some of the recent research our systems have powered. Then we'll show you how you can use it today on Azure Quantum with a quantum machine learning demo. But first, who are we, Sonika?
Hello, everybody. I'm Sonika Johari, a senior applications researcher at IONQ. I graduated with a PhD in theoretical condensed matter physics from Princeton University in 2014. I got into quantum computing by pure chance when I came across a job listing in the area while I was working as a software engineer at Intel. I've since enjoyed working in the field tremendously and now have over 5 years of experience in developing algorithms for near-term quantum computers.
Thanks. And I'm Matthew Keeson, Vice President of Product Development at IONQ. Kind of like Sonika, I became interested in quantum computing initially by chance in high school in the 90s. My physics teacher assigned me a presentation on an experiment recently performed at NIST, where Dave Weiland's postdoc Chris Monroe led a team to perform the first quantum logic gate ever. And now, 20 years later, I worked with Chris at IONQ. IONQ builds trapped ion quantum computers and makes them available on the cloud. And we're excited that you can use our machines today on Azure Quantum. Here's our most recent machine. As a software engineer, this is kind of my dream, a black box with cool lights. And in a few moments, we'll be taking you on a quick tour of what's going on inside. But first, some context. IONQ is based on our founders' decades of research. I mentioned Chris's project back in the 90s. IONQ was actually spun out of Chris and Jungsang Kim's research at Maryland and Duke about 5 years ago. And as an aside, if you're interested in joining us on this journey, please drop us a line as we are hiring. We were stoked to be invited to the Azure Quantum ecosystem. In part, just as democratizing access changed the trajectory of classical computing, we expect that democratizing access will accelerate quantum computing. We're glad that starting yesterday, all Azure users can run programs on real quantum hardware like ours. In addition, Microsoft obviously has a great tradition of programming language R&D, and the Q# language is an awesome way for traditional software developers to start learning quantum programming with a great community and tutorials. So, in a nutshell, how do our systems work? What goes on inside that black box? This is a picture of a gold-plated ion trap, basically a fancy version of the same technology that powers the world's best atomic clocks. We trapped individual ions in an electromagnetic field to service our qubits. Now, this may sound abstract. So here's a video I took last year of 25 atoms floating in space. They're glowing because we're illuminating them with a laser beam, and you can see how they line up. To compute with our ions, we precisely manipulate their quantum state using laser beams, which serve as our wires between quantum logic gates. Addressing our qubits with lasers is much like how you'd address bits in a traditional array. And to demonstrate that, well, you can't actually watch as this happens in real life, since observations collapse quantum states. So here's a visualization of laser beams realizing quantum logic gates on ions as we play through the quantum circuit. There's actually lots of advantages to computing with ions all lined up in a linear trap like this. For one, they're all the same element, so each qubit is identical. Ions are naturally quantum, as opposed to solid-state superconducting qubits that have to be forced into behaving quantumly. Since they're floating in a vacuum, they're also isolated from their environment. And despite that fancy gold plating, you can actually make these traps in a conventional silicon fab. This translates into a few concrete benefits for developers. For one, you can run a gate between any pair of qubits in a system. We call this all-to-all connectivity. Second, you may also have learned that in today's noisy quantum computers, logical operations don't have perfect fidelity. In our system, fidelities of gate operations are both high and consistent across the entire chain. Third, we compile and optimize high-level quantum logic gates into ion-native quantum operations, so you don't have to know anything about ion physics to get great results. In fact, in a recent distinguished paper at POPL 21, our lead theorist's paper was declared the best performing optimizer we know of in terms of total gate reduction. Last, unlike some other systems, our computers calibrate continuously 24/7. Not only are they typically available 7 days a week, depending on volume, but performance is also generally consistent from run to run. And with that context, I'd like to turn it over to Sonika to walk through some examples.
Thanks, Matt, for that great introduction to IONQ. I will take over now and give an overview of recent work on quantum applications at IONQ, as well as show you all a demonstration of running a quantum machine learning example on an IONQ backend via Azure Quantum. On this slide, I've given some examples of how our trapped ion systems have been used to implement a wide variety of algorithms. The application areas here span from chemistry to condensed matter physics to high energy physics, quantum gravity, to more practical things like optimization and search and machine learning. As an example, I will describe a recent demonstration of quantum machine learning on our 11-qubit system in the area of image classification. The average 2-qubit gate fidelity accessible to cloud users on the system on which this experiment was done was more than 96%, and the system consisted of 11 qubits. As we all know, image classification has a wide variety of uses, whether that is to automatically do facial recognition on social media, or identify tumors in MRI images, or help self-driving cars navigate. In this work, we performed image classification on a quantum computer on 2 real-world data sets. The first one consisted of 3 varieties of the iris flower. The second one was the MNIST data set consisting of images of handwritten digits shown on the bottom left over here. In this work, we used the quantum version of a simple machine learning algorithm called the nearest centroid classifier. In this algorithm, we first fit a model by finding the centroids of each class of training data. This is done classically and can be visually seen in the example on the right, where the different colors indicate the different labels of an economic data set. Now, when we're given a new data point and asked to classify it, its label is predicted by computing the distance to all of the centroids and then assigning the label of the nearest centroid. In this case, these distances were computed on the quantum computer. I should mention that this work was done in collaboration with QCware. In our paper, listed in the lower right corner here, we describe circuits that load the classical data into the quantum computer and compute the distances. The special thing about these circuits is that they have depth that is logarithmic in the dimension of each data point. They also have a tree-like structure, which leads to extremely favorable noise resilience properties. Since this experiment was done on a non-error corrected system, we designed an error mitigation technique in which we post-process the histogram output from the circuit to discard states that we knew lay outside the valid subspace in which the algorithm works. This is shown on the right here, and we will see in the next slides that this technique provided enormous increases in the accuracy of the algorithm. Let's look at the results for the iris dataset first. This dataset consists of 3 classes of flowers with 50 samples from each of the 3 classes. Each data point has 4 dimensions that correspond to the length and the width of the sepals and the petals. This dataset has been used extensively for benchmarking classification techniques even in classical machine learning, in particular because classifying this set is not trivial. On the bottom of the histogram here, NQ stands for the number of qubits, NC is the number of classes, and NS is the number of shots. For each case, the blue bars on the left correspond to the results without error mitigation, and the red bars on the right correspond to the error mitigated result. The classical nearest centroid algorithm, shown by the dashed line here, reaches accuracies of around 93%, while our experiments with 500 shots and error mitigation reach 84% accuracy. The figure on the right compares the classification visually before and after error mitigation. Many of the points that lie close to midway between centroids were originally misclassified by the quantum computer, but after applying the error mitigation, they were moved into the right class. Now let's move on to the MNIST database, which contains images of handwritten digits and is widely used as a benchmark for classification algorithms. Each image is effectively a 784-dimensional point. In order to be able to work with this data set, we pre-process the images using principal component analysis in order to project them into 8 dimensions. We then created subsets of this data set as shown here, consisting of samples of 0 or 1, or let's say 2 or 7, and so on. You can see here that after error mitigation, the quantum computer matches the accuracy of the classical classifier for all of the data sets tested. By the way, the accuracy of the classical classifier here is shown by the diamonds. You should note that this is the first time classification with 4 or 10 classes has been performed on a quantum computer, and the accuracies we see here are quite remarkable. And then just a couple of other recent applications, including the first a couple of other recent applications include the first practical and experimental implementation of a quantum classical hybrid generative algorithm capable of generating high-resolution images of handwritten digits. And another one is the use of the quantum approximate optimization algorithm, also known as QAOA, to find solutions of the binary paint shop problem and demonstrate that QAOA with constant depth is able to beat classical heuristics on average, even in the infinite size limit. Okay, now I will move to the demonstration. Okay, so the demonstration we are going to show is how to perform generative learning using a quantum computer. The example we will be showing is based on the 2019 paper, which came out from the group of Chris Monroe, who is one of IONQ's co-founders. The technique we use here in the literature is called DQCCL, which stands for Data-Driven Quantum Circuit Learning. It is a hybrid quantum classical technique for generative modeling of classical data using a parametrized quantum circuit as the model being trained. The training occurs by sampling the output of a parameterized circuit run on a quantum computer and updating the circuit parameters using classical optimization techniques. Convergence produces a circuit that can capture the correlations in the training data and thus serves as a generative model for the data itself. So the data set that we use here is going to be a very simple data set called the bars and stripes data set. So to visualize this data set, you can just see what it looks like for a 2x2 matrix. So basically, each point in the data set consists of either a bar, which is a horizontal row, or a stripe, which is a vertical row. In this case, I've shown it for just a 2x2 matrix, but actually you can imagine extending this to any matrix with, let's say, n rows and m columns, right? Each data point in this data set, it can be encoded as a binary string, and you can see that if the square here is filled, it can correspond to a 1. And if the square there is empty, it can correspond to a 0. So each data point becomes a binary string, right? And then the aim is to train a circuit that produces a probability distribution that produces these binary strings. That only produces these binary strings, firstly, and then secondly, produces all of them with approximately the same probability. So that's basically our goal for learning. Next, let's move on to the implementation of this algorithm. We use in this example, we use a Python library called Noisy Opt for optimizing noisy functions. This is actually in case you're doing any kind of variational quantum classical hybrid algorithm, you should always think about using a stochastic optimizer or some kind of optimizer that works well for noisy functions. That typically leads to much better convergence, which is why we've used that here. Other things that we need to define are a generator that generates samples from our bars and stripes training data set. Then we need a generator for that describes our parameterized circuit, a cost function for our optimizer, and then methods for running circuits on the Azure IONQ backend, and of course the hybrid learning algorithm itself, which uses all of the above. So the first thing you need to do is import all of the Python routines that you need, Python routines and libraries that you need to implement this algorithm. You should also, I also advise importing matplotlib, which will let you produce visualizations inside the notebook. Next, you want to import Q-sharp routines and connect to the Azure workspace, right? And so over here, I should say that the Azure, the Q-sharp functions which implement the circuits have themselves not been implemented in the notebook, but they have been implemented separately in a file, in a file that is a Q-sharp file. It ends with .qs, right? And these basically describe the circuit, and they will be called from the notebook, right? So over here we see that we are connecting to the Azure resource using our resource ID that's provided to us from our Azure workspace, and we are also importing the Q-sharp functions that will allocate qubits and run the circuit. Next, since we're doing an optimization process that will use a random number random number generation, it's always good to fix a seed in order to make the process reproducible in case we need to debug. Over here, first we are going to define the bars and stripes generator, right? And so this is just a very simple function that that produces bit strings that correspond to the two samples from the bars and stripes data set in the way that I described earlier, right? So that's a fairly simple function. Next we will have to describe the circuit generator, right? And so the circuit in this case will consist of alternating layers of entangling of what we would call an entangling layer and a driving layer. And so the driving layer consists of single qubit gates, and the entangling layer consists of 2 qubit gates. And so we first initialize the parameters for the driving portion of the circuit and also the parameters for the entangling portion of the circuit. And then the optimization that happens will actually generate optimal values for these beta and gamma. Next you want to define the cost function, right? And so the cost function is basically just testing how close the probability distribution generated by the quantum circuit is to the ideal target probability distribution. So we've defined it in this way. And then finally, we need some helper methods, right? And so the helper methods will first of all construct the circuit and then run it on the Azure backend. And for this one, we have to be a little careful because since we are connecting to a resource that is remote, we have to account for different eventualities, because sometimes the job can fail or sometimes it can be waiting for a long time. So when you write any kind of hybrid algorithm, make sure that you take all of that into account. And then next, finally, you run the learning algorithm, right? And then you first set up the training data for the problem using all the routines that we defined earlier. So in this case, we are using a very simple example, just a 2x2 matrix. So we set the number of rows to be 2 and the number of columns to be 2. And we define the connectivity of the entangler over here, right? Then we generate the target distribution given the number of rows and columns. And then we check that the expected output is correct. And so you can plot it over here and you can see that that visually it looks like we generated the correct target probability distribution. And then on Azure, you can call 2 kinds of IONQ backends. One is the simulator and one is the QPU. So first, let's test this out using the IONQ simulator. Right, and so over here in the previous run, I invoked that and it said that it was available. Then next we set up the training parameters. So the training parameters consist of things like the number of layers of the in the parameterized circuit. So if you have more layers, the circuit can learn more complex data, but also it will take much longer to train because there are more parameters over which you have to optimize. You can set the number of shots, which is basically how many times the quantum circuit is run in order to calculate the output probability distribution. And then you can decide whether you're initializing the parameters randomly or you're initializing them in some fixed favorable initial state. So you set up based on your initialization preferences, you generate the initial values of beta and gamma, right? You set up some bounds on what values are allowed for your parameters, right? And then we invoke this function, that implements a noisy optimizer, right? And then we basically we deploy it on the IONQ backend, and so then if you print out the output, you'll see things like this, right? So I'm printing out. Since for each optimization, several jobs were submitted and came back. So this prints out the status of each job, right? And you can see this is the cost function after each circuit was run. You can see that in the end, we produced a probability distribution that looked like this. So the ideal probability distribution would actually have been just the states 3, 5, 10, and 12 would have had equal probabilities of 25%. And you can see that the simulator came pretty close to producing a similar probability distribution. It's not perfect. There's still some other states that have finite probability, but it's pretty good, right? And I've also printed out here some of the metrics, right? The minimum possible value of the cost function was 2, and our optimizer converged to a cost function of 2.15. And the number of function evaluations was 20, and the number of parameters we were optimizing over was 5. Right. Next, let's train the circuit instead of just on the simulator. Let's just see what happens if we run it actually on the QPU. Right. And so other than setting this target as the IONQ QPU, everything else was exactly the same. Right. And it proceeds in pretty much the same fashion, except typically there may be a queue for the QPU, whereas for the simulator there's usually no queue. Right. So the answer comes back typically slower from the QPU. But in any case, the optimization proceeded smoothly, and we got a cost function that was higher than that for the simulator, which was to be expected because the quantum computer is not perfect yet. It's not error correct. It still has some noise, but it did converge to a value close to the minimum possible value, right? And you see here the output. So it is noisier than the simulator, but you can still see that the ideal states of 3, 5, 10, and 12 still have high probability of occurring compared to all of the other states. And so that wraps up our demonstration. Over to you, Matt.
Great, thanks, Sonika. Put our contact info up. If you have any further questions, we'll be in the chat, and also feel free to tweet at us or email us. And we really appreciate you attending our session.
Thanks, everyone.
All right, well, I will talk to you probably. All right, thank you, Matt and Sonika, for that very interesting walkthrough of how IONQ's hardware implements quantum logic gates and some sample applications using your system. Now, Matt, I have to say, I am so jealous that you can say, here's a video I took of these 25 atoms floating in space exactly where I wanted them. Now, after watching the quantum machine learning example learn the bars and stripes dataset, you may be wondering, how can you learn your stripes in quantum? Well, have I got a solution for you? Yesterday, with the announcement of the public preview of Azure Quantum, we made available the Quantum Computing Foundations Learning Path in Microsoft Learn. Now, this is awesome content, and our team has been working so hard on putting this together. It starts with everything that you need to know to get started with Azure Quantum, so you can create your first Q# program by using the Quantum Development Kit. It teaches you the basics of Q# and quantum programming. It explores some key algorithms such as Grover's search, and then shows you how to get started with Azure Quantum and actually apply that knowledge to run on real quantum hardware. And then lastly, it goes into detail on optimization. So you can learn how to take a real world use case and solve it using the optimization solutions from Microsoft and 1QBit in Azure Quantum. This is really great content. It's a ton of fun. It's high quality, and it's freely available. So you can check that out at the link on screen. It's aka.ms/aq/learn. And I've just been told that that the link was flipped. So there you go. That's fixed. Again, it's aka.ms/aq/learn. And I'll see if I can get a moderator to post that into chat for a little bit later. Now, next up, I'll be handing things over to my colleague Dan Stalker, who will be talking about Microsoft's quantum-inspired solutions provider available in Azure Quantum. But before I do that, I wanted to remind you one more time that at the end of the workshop, we'll be hosting a panel of experts for a live Q&A session where we'll be pulling questions from the live event Q&A. So be sure to ask if you have any questions. We'll be answering the most pressing questions that we haven't gotten to by then at that time. So with that, let's go ahead and hear from Dan about the Microsoft quantum-inspired optimization solutions available today in Azure Quantum.
Hello and welcome to our Microsoft Showcase. Today we're going to cover the Microsoft optimization offering inside Azure Quantum. My name is Daniel Stocker and I'm a program manager on the Azure Quantum team. Today I will build on some of the content that we have shared with you at our earlier Azure Quantum Developer Workshop and talk about the various solvers that we have available and how you pick the best one for your problem. Let's get started. Let me begin by telling you a little bit about me. I'm a program manager in our team, and I spent a lot of time talking to our customers about their optimization problems, but also work closely with the solutions and service teams who've built the very service that we're going to be looking at today. As we explore this optimization offering, it's so much easier if you can relate it to a real industry problem, which is why we're going to use a proper industry problem today. I'm also excited to share with you that our MS Learn resources have been updated to cover this problem. So if you want to go off after this session and build it yourselves, you're more than welcome to do that. Once we have defined our problem and understood the offering, we want to look a little bit more closely at our solvers. And I'll take you through a multi-step process of picking and tuning a solver. Finally, we'll finish off with a summary and some next steps on what you can do to learn more. Let's get started. I want to begin with a quick overview of the optimization offering itself. Our optimization solvers allow you to solve binary optimization problems in the cloud. Any problem that runs on the service requires us to develop a cost function using our SDK, and to pick a solver to then use that cost function to solve your problem. As you define these, you've got two different problem formulations at your fingertips. There's the Ising model and PUBO. The Ising model is based in physics and represents a set of magnetic spins as either +1 or -1. The PUBO model uses pure binary, and variables can therefore be in two discrete states, either 0 or 1. For today's demo, we're just going to use PUBO, but Ising works very similarly. Like I said, the zeros and ones represent our problem's variables. Our provider offers a range of solvers that you can pick from, and we'll go through all of them later on in the session. The solver's job is to modify the zeros and ones in the starting configuration that you see in front of you. It continues to modify this configuration until it's found the lowest possible cost. The cost function defines a set of constraints and objectives. This is what the solver uses to calculate the cost of the solution whenever it makes a change. The arrows in the diagram, they are showing floating point coefficients between each term in that configuration. With all these definitions in mind, as we send a job to Azure Quantum, we need to be really clear about what problem we're trying to solve. In order to define a problem, we need to first understand its mathematical representation. And we can use our SDK to define it in code. This produces the cost function. We use the same SDK to select the solver that we want to use, and then we send everything off to Azure Quantum. A solution is returned in a general format, and it's up to us as developers to turn this solution into something useful for our client or our business. Our solvers are building blocks that can apply to a range of different scenarios and use cases because they are general, and they're here to enhance your solution with the optimization power of Azure Quantum. With that in mind, let's define our problem for today. We're going to be looking at job shop scheduling. For those of you who don't know, it's a problem that is grounded in manufacturing. But scheduling more generally is a very common problem, as we all know. With job shop scheduling more specifically, what we're trying to do is we're trying to make sure that within a factory, we use our machines and resources as effectively as possible, meaning that we minimize the time to make a set of products while also maximizing the use of each individual machine. Let's look at an example. In this example here, I've got 3 machines that need to build 4 different products. And the different products are all classed as a job. Each job breaks down into several operations. Let's look at this in a different way. You can see here that different products require different sets of operations to be built. All operations need to happen sequentially, and certain operations can only be performed by certain machines. We can see in this example that the first machine is required for the second and the third job. With a small problem like this, it's fairly easy to put a chart together yourself that just shows when which machine should be used. But this very quickly becomes very complex. Let's look at an example. Here I've created a Gantt chart myself based on the machines, the jobs, and the operations. You can see that every line is an operation. You can see that each operation happens in turn, and the jobs happen in parallel. If you look at this grid, you can see that every field in it is a time step, and we can see that we complete all jobs within 7 time steps. This is what we call the make span. It's the time that all jobs take to finish, and we want to keep this as short as possible in the job shop scheduling problem. We need to do this, though, while complying with all production rules. And these are some of the things that I've just explained. Like, for example, you have to complete each option in turn. Now, if we overlay the binary grid, we can see how we would represent this problem in binary. Once again, we know how many operations we have, we know what order they occur in, and we know how many jobs we have. This is the job of the developer to remember. We can then come up with this problem definition here, where we've got a 1 in each line that signifies when an operation starts. As you can see, different operations take different amounts of time steps. Now that we have a problem definition in binary, what else do we need to do to build our cost function? Well, this is where the maths comes in. Our next step is to go through the literature. Job shop scheduling is very well defined, so we can find plenty of examples on the internet or in academic papers. This helps us find mathematical definitions of the production rules, or in this case, constraints that we want to implement. Let's go through the constraints in turn. Like I mentioned, we want to make sure that each machine can only do one thing at a time. We also want to ensure in our schedule that operations within a job happen in order. We also need to make sure that each operation only starts once, because otherwise the schedule isn't valid that we get at the end. Now, if we were to just implement these 3, we would very likely get a valid schedule out of Azure Quantum. But what we also need to do is implement our objective, which is this reduction of the make span that I talked about. Altogether, we express the maths in code and create a cost function that we can send up to our optimization provider inside Azure Quantum. Here we have an example of what this looks like. I have implemented the constraints in a Python file, and I'm running a demo with that Python file. It compiles my cost function and sends it up to Azure Quantum and gets a result. Let's look at this a little bit more closely. You can see here that I implement my free constraints and my objective. These are separate calls that go out and produce a bunch of terms. I add all the terms together, and then I send them off as a problem definition in Pubo to a solver. In this case, it's parameter-free simulated annealing, and I let it run for 100 seconds. If I look inside the Azure portal, I can see a set of inputs and outputs that I can further explore. Let's have a look at those. In the input, I can see what my cost function looks like as it gets sent to the service. I can also see my output. Now, how do I turn this output into a production schedule? Let's have a deeper look at that. Here is what we get back from the service. It's just a single dimensional array with ones and zeros. Like we explained previously, each line in our production schedule is an operation, and we know how many operations we have. So it's easy to divide that array into a multi-dimensional array, and then implement a schedule visualization like the one shown. Again, remember that our optimization solvers are building blocks. It's up to us as developers to infuse our solutions with them. The bit string alone is not very helpful, but by leveraging the optimization capabilities inside Azure Quantum, you can build very rich solutions that solve your clients and your organization's problems. Now we've solved our problem, but we're not done yet. We haven't actually looked at what this solver does under the hood, and whether simulated annealing, or specifically parameter-free simulated annealing, is the right choice for our problem here. Is it really the best option? Now, let's look at that in a bit more detail. I want to unpack best specifically, because what does best mean? And the definition of best really depends on your business requirements. We might also call that a benchmarking objective. And you get your benchmarking objective by really listening to your customer, by really listening to your business, or just generally your client. I have a few examples here of what you might pick as a benchmarking objective, but let's put them into context for job shop scheduling, because we've just been working through that problem. The first example that I have here is return a feasible, good solution within 5 minutes. You might only have 5 minutes to create your schedule. You might have loads of machines. So you need to get the best possible result within 5 minutes. If that's your benchmarking goal, you will try different problem instances with large schedules across different solvers to see which one gives you a good solution in the smallest amount of time. You may also already have a scheduling solution that produces a result, but it might not be very good. It might include lots of conflicts, and you might want to reduce the amount of conflicts. In that case, you maybe don't care so much about which solver returns first or how much time you're giving it. You just care about the solution quality, and you want to compare that. So that's a completely different benchmarking objective. There's also a hybrid between the two, where you might say, within a reasonable time, you want a good set of results for certain problem instances, and that's fine. In order to get there, you need to define your problem instances first, and then benchmark against them with different solvers. And that's another very valid benchmarking objective that you can use. Now that you have a benchmarking objective, we can start evaluating. Let's go back to our solver here. We can see that the parameter-free version of simulated annealing has returned some parameters for us that we can use. And we're going to look at how simulated annealing works in a bit more detail. The reason we do that is so that we can better understand what the algorithm does, and we can better tune our problems towards this algorithm and our other solvers. With all of our optimization solvers, tuning works very much like tackling an ML problem. Like with ML, you have to explore, review the literature, search online if somebody solved the problem before. It is more an art than a science in many cases, because your problem formulation and the solver and problem instance combination is very important to how the solver performs, together with the parameters. Now let's look at the simulated annealing parameters in a bit more detail. We've got 4 parameters here: beta start, beta stop, which defines a temperature, sweeps, and restarts. Let's look in a bit more detail as to what that means. Simulated annealing does what it says on the box. It simulates an annealing process. It does so by using a walker that traverses our configuration. The beta start and beta stop parameters define the starting and the stopping temperature. As we go through our sweeps, the temperature decreases. At a high temperature, the walker is very likely to take a configuration that has got a higher cost in the hope that it'll find a better optimum later on. As the temperature decreases, it'll be less likely to do so and might get trapped in a local optimum. In order to avoid reporting out a local optimum when this algorithm returns, we need to run a bunch of restarts. The hope is that over time, we'll discover better optima that we can report back on. Let's look at a quick simulation of this in action. At the start, you can see the walker move around quite a lot and also take moves with higher cost very frequently. As it cools down, you see that behavior reducing. In this case, it lands in a fairly good optimum from what we can see here. Now, we have run simulated annealing in the parameter-free version, which picks the parameters for you, but they are based on your specific problem instance. And it's very unlikely that you're only going to solve one problem instance with a solver. Generally, you want your solution to apply to more than one specific problem. So therefore, parameter-free solvers are a really good starting point to give you some example parameters that you can tune further. Be aware that parameter-free solvers do have an overhead because they need to figure out the parameters before they run. So you usually get much better performance by using parameterized solvers. That's not to take away from the fact that it's a really great starting point. And speaking of starting points, here's a few steps that you can take as you start to experiment and explore your problem. We would recommend that without any other prior knowledge, you would begin with parameter-free simulated annealing to find a first baseline. You can compare that with parameter-free parallel tempering. It's actually really easy to kick off both at the same time. It's just an extra line of code if you want to do that instead. We will go through the difference between parallel tempering and simulated annealing in just a moment. As you've worked on the parameter-free solvers, you can evaluate and see which one performs better and which one you want to pick as your baseline. You can then evaluate parameterized versions of these solvers and work towards achieving your benchmarking objective with further problem instances. As you learn more, you can expand to our wider solver offering and use other solvers like Taboo Search or FPGA-based solvers, which we'll cover later on in the session. Now, as I mentioned, let's cover what parallel tempering is and how it is different from simulated annealing. As with simulated annealing, we will explore the cost function through thermal jumps. Simulated annealing does this on one configuration. However, unlike simulated annealing, we do not use the cooling temperature that we use in simulated annealing. That's why in parallel tempering, we take several copies of the configuration. We call these replicas. They are randomly initialized at different temperatures. Then the same process as in simulated annealing happens, but based on the specific protocol, two replicas can be exchanged between different temperatures. This change can enable walkers that were previously stuck in local optima to be bumped out of them. It encourages a wider exploration of the problem space. Based on what your problem looks like and what your cost function is like, either parallel tempering or simulated annealing might perform better. So it's because of that you should use both to create a baseline. Having developed your baseline, we go into the stage of further tuning. I've mentioned previously that you want a good set of problem instances. This is really important because if you work off just one problem, you might get a really, really good combination of parameters for that one problem, but you might not be able to solve any other problems with great efficiency. Speaking of efficiency, you might want to explore our FPGA solvers. FPGA stands for Field Programmable Gate Array. And they are very specialized hardware which are highly optimized for parallel execution and ready for higher memory optimization. This new hardware has got some limitations, and I would strongly encourage you to check our documentation to see if FPGA is worth exploring for your problem. I'll cover a few more limitations, but also incentives for using FPGA on the next slide. Make sure you take advantage of our concurrent jobs feature. The Azure Quantum Optimization Provider, like all of our other providers in Azure Quantum and like many other Azure services, is a cloud-based service and heavily encourages experimentation. If you want to use all your concurrent jobs to run experiments at the same time, that's actually a really good idea because it allows you to run several problem instances at once. Our SDK has a few functions for you that can help with the testing. You might want to upload your problem if it's fairly large. That means it doesn't have to be transferred over the network each time. You might also want to serialize your problem to reuse it later. Let's have a quick look at that solver offering then. As previously mentioned, we currently offer two different hardware platforms for our optimization solvers. We have traditional CPU-based solvers, and then some of them are also available on FPGAs. Like I mentioned, FPGAs are highly specialized hardware. Solvers running on them will use the same parameter types as their CPU equivalent, but may scale differently based on the problem in your scenario. It's important you complete an extra cycle of tuning for that. For example, we've just gone through the restarts and simulated annealing, if you remember. On FPGA, there's basically no point to set restarts under 200 because the hardware already allocates 200 parallel pipelines for your run. So you may as well give it 200 restarts. FPGA solvers also have an initialization time. This means that for problems that take a long time to solve on a CPU solver, they're still quite a lot faster. But for very small problems, you might be better off running them on a CPU. And this is something that is best benchmarked with a couple of problem instances to make absolutely sure. We've also got some more specialized solvers in our offering. Taboo Search looks at neighboring configurations while keeping a taboo list of variables that were already explored. It can accept worsening moves if no improving moves are available, and works well on cost functions that have a fair degree of convexity. It is more efficient there. Quantum Monte Carlo is another solver that we offer, and it works similar to simulated annealing, but the moves are facilitated by emulating quantum tunneling through barriers, rather than the thermal jumps that we explored earlier today. This gives it an advantage for very small and for very hard and small problems. We continue to work on this offering, and as we go into our preview, we look forward to receiving all your feedback on these solvers. And it'll be really great to have your input as we evolve this offering. Now, we've been through tuning, and I just wanted to cover the steps that we've gone through today in a bit more detail again. At the start of this session, we defined our job shop scheduling problem, and we did so in the PUBO formulation. We talked about the fact that to create a problem definition, we often need to consult existing resources. This helps us find mathematical representations of a problem, and it helps us express that representation in our SDK so that we can send everything off to Azure Quantum. Our literature review should also feed into defining the benchmarking objectives that we're going to use to evaluate our solvers. And similar to an ML model, we'll start with parameter-free solvers to get an idea of what good parameters are for our first problem instance. And then as we expand, we continue to benchmark against our solver offering with the set of parameters that we have discovered. This helps us build good baselines, and continuously evaluating against our benchmarking objective, we, through experimentations and structured benchmarking, we find a good starting point towards a solution that performs well. After doing some initial research, we can expand our search to the further solver offering, try offerings like FPGA and our wider offering in general. As with everything, don't forget to tune and benchmark as you go along to have the best possible outcome for your solution. When done right, our optimization service offers you the capability to include powerful problem solving into your applications and solutions. I hope this talk today was helpful to you. And if you want to get started, please do not hesitate to use any of the resources on the slide right now to start learning. Now that you know more about using our optimization service, picking a solver, and tuning it to your use case, we're so excited to see what you will build with the optimization offering. We hope you try our service in public preview, but we're even more excited about the solutions that you will build for your organization, colleagues, and industry going forward. Thank you so much for your attention today, and enjoy the preview.
Thanks, Dan. I really appreciated the walkthrough, and being a QIO novice myself, I appreciate you walking through how to find a solver that works best for your particular problem. Now, there's indeed an art for that. As a reminder, everyone watching can try the Microsoft QIO solvers that Dan showed, as well as the solvers from our good friends at 1QBit today in Azure Quantum. Now, one of the other really interesting things that Dan covered is the process of problem formulation. Now, this refers to the process by which you express a real-world problem as a PUBO or an icing problem in the case of optimization in Azure Quantum. And there's a lot to learn when you do that. And as Dan mentioned, you start with your problem and you can reference literature and you start by exploring that problem space. But if you haven't done that before, it can be a little bit daunting. So with the release of our documentation yesterday, we've also worked on making some really high quality samples of this and the process by which you can start formulating problems. And one of those basic samples is the shipping sample problem, which is good kind of 101 level content. And it's going to walk you through the basic formulation of a real world problem through optimization and some of the kind of key things that we do to help make the problem easier to solve and get better solutions. We also have other samples like job shop scheduling as well, which are also available as Microsoft Learn modules. So if you're interested in optimization, this is a really great place to get started. And again, I'll see if I can get a link in chat, but this is available through our optimization documentation. So you can start with the optimization quick start on the Microsoft Docs site. That'll point you to GitHub, where we do host all of our code samples for optimization. Now, next we'll be going into our second break of the day. And I don't know about you, but I'm going to be applying a caffeinated beverage gate, otherwise called a C-Hot, in order to prepare the optimal learning state to hear from our experts when we get back. I'll see you in about 30 minutes. Thank you so much.
We are really excited to engage with Microsoft on Azure Quantum because we know that quantum provides a path to solve the most complex optimization problems, and that's important to our future.
70% of the goods in the US are moved by trucks today. Trimble is engaged with the transportation industry for many years. We have domain experts from supply chain to routing optimization and fleet utilization. This, together with the sensors data that we get from Trimble equipment, deliver the required information for the solutions that we are developing.
The primary friction is really the movement of data in real time.
Azure Quantum offers a mechanism to do that in a way that we could not do in the past.
We are aiming to a point where the data we collect becomes knowledge and real-time insight.
If that information and that knowledge is available to the shipper, then the shipper can look at alternative carriers or look at alternative shipping plans and meet its objective, maybe a lower rate, lower cost to move the goods, and a carrier gets to increase its utilization.
Not just some destinations we are trying to connect. There are a number of other parameters that come into making an optimal route when we connect a shipper and a carrier. There are hundreds of thousands of connections to be made. And finding the most optimal one is definitely a very hard problem to solve.
Considering the complexity, we envision that quantum technology will play a crucial role in the industry optimization journey.
What's challenged the industry has been the expectations of the consumer. With the pandemic, we've seen the acceleration of e-commerce. It multiplies the complexity of the supply chain. The power that we now have available to us and the data that we have available to us is so much more than what we had before.
One of the things that really gets us excited with Azure Quantum is that it gives us an opportunity to start to engage and bring our domain to talk about these problems and the complexity, and work with a team that is not only building quantum-inspired algorithms, but is actually working to provide a pathway for companies like Trimble to engage in fully enabled quantum optimization.
And we were solving such small problems before with computers. Today, the sky's the limit.
The Microsoft Quantum program is a global scale program focused on enabling commercial scale quantum computation. It's really about bringing quantum impact to people today and tomorrow.
Quantum computing has the opportunity to make an impact on the world right now in a revolutionary, game-changing way.
We're focused on developing every element of the quantum system, an end-to-end full-stack technology from the algorithms to the software stack to the hardware itself. To reach a commercial scale quantum computer, it requires revolutionary discoveries across physics, computer science, mathematics, material science,
all of which have to come together to make topological qubits and multi-topological qubit systems. We have a team that's spread across 8 labs around the world. Although we're spread out, we are one team working towards one goal.
Building a quantum computer is a huge task. It's all the way from the software all the way down to where we control the quantum states that makes up the qubits.
Here in the lab, we have fabrication technologies, nanotechnology, that allows us to turn dumb materials into smart devices.
The Microsoft Quantum program allows us to dream big. We need to dream big.
Azure is the world's computer. You have access to the tools, services, and solutions in a very familiar environment. And with Azure Quantum, we're bringing quantum solutions forward to that environment. We're bringing quantum impact to your fingertips. We're working with enterprises and companies around the world, energy optimization, risk and financial analysis in medical diagnostics, to identify where quantum solutions will bring about impact for their businesses. A great example is Case Western Reserve University.
We're working with Azure Quantum to optimize the way that people get MRI scans. Patients have access to faster and better MRI scans in a way that wasn't possible before.
We can make those scans up to 3 times faster by using quantum solutions on classical hardware today.
The really high-level scientific goal is to be able to solve problems that we can't solve today.
Azure Quantum enables every developer, every person, every enterprise to really tap in and succeed in their businesses and their endeavors with quantum solutions. And that's incredibly powerful.
If you think about MRI today, the problem is that it takes a while to scan. The other problem is that the MRI scans that we do today have limited sensitivity. So we can see some diseases, but there are other diseases that we can't. Our laboratories developed a new way to do MRI scans called magnetic resonance fingerprinting.
In general, we want to make the MR scan faster and more robust, meaning that we can get good result consistently, no matter where the patient is scanned.
Azure Quantum has really inspired us to look at the future. In every fingerprinting scan, there's actually thousands of decisions that we have to make in order to set up the right scan. Surprising, but the scale of that optimization problem is beyond what we can solve with conventional computing.
Conventional optimization algorithms, typically they have some assumptions. For example, they assume that scanner system is perfect or patient in the perfect position. But in reality, there are lots of confounding factors that may change the signal. If the algorithm does not consider all this, then the result may not be optimal.
We're working with Azure Quantum to use their quantum-inspired algorithms to start to solve these problems.
We provide the question and the target, and they're using their algorithm to help us to find optimal results.
Working with Azure has given us improvement in speed and about a 30% improvement in our precision. The results we're getting are allowing us to see diseases earlier than before and to quantify the treatments that we're giving. Working with Azure Quantum has enabled us to do things that we just couldn't do before. It's really changed the way that we think about MRI scans, and we see a whole new world of possibilities that we didn't before. These results from the quantum-inspired algorithms are going to impact the healthcare of billions of people worldwide.
At Ford Motor Company, Quantum is a new initiative. This is probably defining the future landscape of the entire computing industry. Right now, every car is a moving computer. A huge amount of computations are being performed in vehicle or via the cloud.
Quantum's really promising for how it can solve problems that haven't been traditionally solved before. We are looking at ways now that we can take some of the concepts from quantum and apply them to problems we have today.
In our collaboration with Ford, they bring to us physicists, computer scientists, engineers with years of experience in the automotive industry. And we are bringing mathematics, physics, computer science, algorithms expertise to forge a solution. It's really a team effort. So in building our techniques for the automotive industry, we rely on quantum-inspired optimization. It is developing new quantum algorithms tailored to their difficult problems and simulating them on today's computers.
With Ford, we are looking at all the possible ways of how quantum can help them.
One of the use cases that we explored in the phase 1 is a congestion mitigation problem where you have a bunch of cars requesting for routes at the same time and planning to share the same route segment in a city. Under the current technology, there's a selfish routing algorithm that works, where you actually assign routes to each of the vehicles so that they can optimize their travel time without even being worried about how many cars are planning to share the same route segments, which actually creates a congestion.
What we've seen with bringing quantum-inspired optimization to the traffic optimization problem is we can solve these problems in some cases multiple orders of magnitude faster than can be done with conventional electronics. And that could really have an impact on people's everyday lives.
We have the vision in terms of what can drive the future of not only the automotive, but also the future of computing.
It's really great to see how ideas that until recently were just used in academic contexts could be applied now and useful for its products.
We're just scratching the surface with looking at traffic optimization. We see opportunities across the spectrum in automotive, everything from traffic, thinking about mobility as a service, to things like design of better materials and new types of batteries. The possibilities really are endless.
The automotive industry is unique in that it's got really high volumes and touches people every day. So even changing small things for the better make huge impacts both in to our business as well as to our customers.
Willis Towers Watson covers actually an amazing range of services. They're all around, though, the issue of people and risk.
One of the things that sets Willis Towers Watson apart is the use of advanced technology to solve client problems.
Engagement with Microsoft started where we wanted to work with them on the idea of quantum computing, preparing for quantum computing by starting off with what we call quantum-inspired computing today. This is a breakthrough that is going to provide incredible computational power and a different way of really computing.
Risk modeling is a little bit different to classic big data AI sort of problem. With risk modeling, you're trying to quantify the whole distribution of outcomes. It requires quite a lot of specialism, and the prevalent technique is something called Monte Carlo simulation. Simply put, we roll the dice lots and lots of times and calculate from the resulting outcomes.
Quantum-inspired optimization leverages the principles of quantum physics to solve optimization problems in a faster to higher accuracy.
Currently, we can run sort of realistic models in 10 or 15 minutes. If we can bring that down to seconds, then immediately that's opening up the door to real business value.
What this means for the end user is we give them information and insights that they were never able to have before. The limits of traditional computing just meant that we couldn't analyze certain things. With greater insights, then comes more efficiency and better choices. I love the quantum-inspired computing, partly because of the problems that we're going to be working through with Microsoft today, but perhaps more because of what we'll do in the future. The problems we're tackling today, we'll get some great insights and some great results from them, but there'll probably be things that we haven't even begun to think about today that'll give us future results. That's what's really exciting.
At Ford Motor Company, quantum is a new initiative. This is probably defining the future landscape of the entire computing industry. Right now, every car is a moving computer. A huge amount of computations are being performed in vehicle or via the cloud.
Quantum is really promising for how it can solve problems that haven't been traditionally solved before. We are looking at ways now that we can take some of the concepts from quantum and apply them to problems we have today.
In our collaboration with Ford, they bring to us physicists, computer scientists, engineers with years of experience in the automotive industry. And we are bringing mathematics, physics, computer science, algorithms, expertise to forge a solution. It's really a team effort. So in building our techniques for the automotive industry, we rely on quantum-inspired optimization. It is developing new quantum algorithms tailored to their difficult problems and simulating them on today's computers.
With Ford, we are looking at all the possible ways of how quantum can help them.
One of the use cases that we explored in the phase 1 is a congestion mitigation problem where you have a bunch of cars requesting for routes at the same time and planning to share the same route segment in a city. Under the current technology, there's a selfish routing algorithm that works, where you actually assign routes to each of the vehicles so that they can optimize their travel time without even being worried about how many cars are planning to share the same route segments, which actually creates a congestion.
What we've seen with bringing quantum-inspired optimization to the traffic optimization problem is we can solve these problems, in some cases, multiple orders of magnitude faster than can be done with conventional electronics. And that could really have an impact on people's everyday lives.
We have the vision in terms of what can drive the future of not only the automotive, but also the future of computing.
It's really great to see how ideas that until recently were just used in academic contexts to be applied now and useful for your products.
We're just scratching the surface with looking at traffic optimization. We see opportunities across the spectrum in automotive, everything from traffic, thinking about mobility as a service, to things like design of better materials and new types of batteries. The possibilities really are endless.
The automotive industry is unique in that it's got really high volumes and touches people every day. So even changing small things for the better make huge impacts both in to our business as well as to our customers.
Willis Towers Watson covers actually an amazing range of services. They're all around, though, the issue of people and risk.
One of the things that sets Willis Towers Watson apart is the use of advanced technology to solve client problems.
Engagement with Microsoft started where we wanted to work with them on the idea of quantum computing, preparing for quantum computing by starting off with what we call quantum-inspired computing today. This is a breakthrough that is going to provide incredible computational power and a different way of really computing.
Risk modeling is a little bit different to classic big data AI sort of problem. With risk modeling, you're trying to quantify the whole distribution of outcomes. It requires quite a lot of specialism, and the prevalent technique is something called Monte Carlo simulation. Simply put, we roll the dice lots and lots of times and calculate from the resulting outcomes.
Quantum-inspired optimization leverages the principles of quantum physics to solve optimization problems in a faster to higher accuracy.
Currently, we can run sort of realistic models in 10 or 15 minutes. If we can bring that down to seconds, then immediately that's opening up the door to real business value.
What this means for the end user is we give them information and insights that they were never able to have before. The limits of traditional computing just meant that we couldn't analyze certain things. With greater insights, then comes more efficiency and better choices. I love the quantum-inspired computing, partly because of the problems that we're going to be working through with Microsoft today, but perhaps more because of what we'll do in the future. The problems we're tackling today, we'll get some great insights and some great results from them, but there'll probably be things that we haven't even begun to think about today that'll give us future results. That's what's really exciting.
We are really excited to engage with Microsoft on Azure Quantum because we know that quantum provides a path to solve the most complex optimization problems, and that's important to our future.
70% of the goods in the US are moved by trucks today. Trimble is engaged with the transportation industry for many years. We have domain experts from supply chain to routing optimization and fleet utilization. This, together with the sensors data that we get from Trimble equipment, deliver the required information for the solutions that we are developing.
The primary friction is really the movement of data in real time.
Azure Quantum offers a mechanism to do that in a way that we could not do in the past.
We are aiming to a point where the data we collect becomes knowledge and real-time insight.
If that information and that knowledge is available to the shipper, then the shipper can look at alternative carriers or look at alternative shipping plans and meet its objective, maybe a lower rate, lower cost to move the goods, and the carrier gets to increase its utilization.
Not just some destinations we are trying to connect. There are a number of other parameters that come into making an optimal route when we connect a shipper and a carrier. There are hundreds of thousands of connections to be made. And finding the most optimal one is definitely a very hard problem to solve.
Considering the complexity, we envision that quantum technology will play a crucial role in the industry optimization journey.
What's challenged the industry has been the expectations of the consumer. With the pandemic, we've seen the acceleration of e-commerce. It multiplies the complexity of the supply chain. The power that we now have available to us and the data that we have available to us is so much more than what we had before.
One of the things that really gets us excited with Azure Quantum is that it gives us an opportunity to start to engage and bring our domain to talk about these problems and the complexity, and work with a team that is not only building quantum-inspired algorithms, but is actually working to provide a pathway for companies like Trimble to engage in fully enabled quantum optimization.
We were solving such small problems before with computers. Today, the sky's the limit.
The Microsoft Quantum program is a global scale program focused on enabling commercial scale quantum computation. It's really about bringing quantum impact to people today and tomorrow.
Quantum computing has the opportunity to make an impact on the world right now in a revolutionary, game-changing way.
We're focused on developing every element of the quantum system, an end-to-end full-stack technology from the algorithms to the software stack to the hardware itself. To reach a commercial scale quantum computer, it requires revolutionary discoveries across physics, computer science, mathematics, materials science,
all which have to come together to make topological qubits and multi-topological qubit systems. We have a team that's spread across 8 labs around the world. Although we're spread out, we are one team working towards one goal.
Building a quantum computer is a huge task. It's all the way from the software all the way down to where we control the quantum states that makes up the qubits.
Here in the lab, we have fabrication technologies, nanotechnology, that allows us to turn dumb materials into smart devices.
The Microsoft Quantum program allows us to dream big. We need to dream big.
Azure is the world's computer. You have access to the tools, services, and solutions in a very familiar environment. And with Azure Quantum, we're bringing quantum solutions forward to that environment. We're bringing quantum impact to your fingertips. We're working with enterprises and companies around the world, energy optimization, risk and financial analysis in medical diagnostics, to identify where quantum solutions will bring about impact for their businesses. A great example is Case Western Reserve University.
We're working with Azure Quantum to optimize the way that people get MRI scans. Patients have access to faster and better MRI scans in a way that wasn't possible before.
We can make those scans up to 3 times faster by using quantum solutions on classical hardware today.
The really high-level scientific goal is to be able to solve problems that we can't solve today.
Azure Quantum enables every developer, every person, every enterprise to really tap in and succeed in their businesses and their endeavors with quantum solutions. And that's incredibly powerful.
Hi everyone, and welcome back to the Azure Quantum Developer Workshop. I hope you've had a chance to rest and relax, and you're ready to hear from our panel of experts with the answers to your questions. As a reminder, throughout the workshop today, we've been collecting the top questions from the audience to share with our experts. Now, as a quick aside, earlier in my career, I attended a talk by a distinguished engineer here at Microsoft, and he gave the advice that if you want to set yourself up to learn, make sure that you're never the smartest person in the room. Surround yourself with experts, and that's the most effective way to learn a difficult subject. And looking at our roster of speakers today, I can without a doubt look back and say, James, I did it. So without further ado, I'd like to introduce our venerable panel of experts. Matt, if you could advance the slide, thank you. So I'll just read through and introduce, but I think there'll be some familiar faces from earlier in our workshop. First off, from 1QBit, we have Valentin and Rudy, who will be here to answer questions about 1QBit's offerings. Next up, we have Brian Nienhaus from Honeywell, who's the commercial operations leader there. From IONQ, we have our speakers, Sonika Jory and Matt Kisan, who will be able to answer your questions about their solutions. And then lastly, from the Microsoft side, we have Stephen Jordan, a principal researcher, and Chris Granade, a senior software developer. Thank you and welcome to our experts. Now, the format of the panel today is going to be pretty simple. We've been collecting questions from earlier, and I'll start by directing some of these questions to some of our experts. Now, Matt, I believe you prepared the first question for us today. Okay, to start off, for Valentin at 1QBit, why do we even need a quantum computer if we can split the initial problem into problems that are so small that a classical computer can handle them? Valentin, are you able to help answer that?
Hello, yes, this is Valentin. That's an interesting question. I think that's a very valid one. So the idea behind these techniques we use for approach these quantum chemistry problem is that, you know, instead of tackling head on a very large problem that would require an amount of resources that we may not have today or have in the future at all, we split that into like smaller problems, and then we go on and we solve them. Actually, it's to be able to leverage the quantum computers of today, which are still very experimental, the fact that we can make a real interesting problem amenable to some of them is interesting. And as the capabilities of the machines grow, then we may need to decompose this problem less and less until maybe one day we have a quantum computer that can very efficiently, much more efficiently than classical hardware, tackle these problems head on or less decomposed.
Sorry, I was muted. Can you speak just a little bit more about kind of the advantages that you see once you're able to solve the whole problem as a single problem with a quantum computer?
Sorry, can you repeat that one more time, please, the beginning of your question?
Sorry, I was just asking, are you able to speak a little bit more about the advantage that you see once you can actually handle that problem in a single instance instead of many sub-problems? You mentioned it's a bit more efficient.
So essentially, because we think quantum computers are good candidates to solve very efficiently quantum chemistry problems because of the quantum nature, the underlying quantum nature of particles, right, which maps to qubits. Essentially, instead of having kind of like an exponential amount of resources required, and so resources, computation and memory with classical computers to treat these problems, there would be a kind of like a linear mapping on quantum computers with a drastic reduction in the amount of operations. That's why we think they're well suited. So as soon as quantum computers grows in terms of capacity, they should quickly catch up in terms of capacity to the classical equivalents.
That's very interesting. Thank you. Matt, do you have our next question? Okay, for IONQ and Sonika specifically, what should the developer community use the IONQ system for? Do you have any advice or directions for our audience members to get started?
Hi, yes, thanks. For those of you who saw the video, you know that I mentioned that so far problems from machine learning, optimization, search, quantum chemistry, condensed matter physics, quantum gravity have been run on the IONQ system. So really, it's been applied to a wide variety of problems. So we would really encourage the developer community to be ambitious and creative in what they use our systems for. Especially in the fields of machine learning and optimization and quantum chemistry, there are a wide variety of application-focused libraries that are now developing, and we would really encourage users to sort of start testing the circuits from those libraries on our systems and really push the limits of what's possible. Thanks.
Thank you. Yeah, that seems like a really great starting point, and something that I think that Q Sharp and our ecosystem and community are really well positioned to help people get started with. So that's really interesting. Thank you. Matt, do you have our next question ready? Perfect. Thank you. For Brian at Honeywell, how can you make sure that you don't make excessive noise and affect the qubit state while moving qubits around? Can you talk a little bit more about that, how that's done in hardware?
Yeah, of course. So as I talked about earlier in my presentation, the qubit states are held in two different hyperfine states of our ion. And so what this physically means is whether it's a 0 or a 1, that means the spin of the nucleus and the spin of the electron are either aligned or anti-aligned. And luckily for us, this is very well decoupled from the motion of the ion. To flip the spin of either the nucleus or the electron is actually a tricky thing to do. It takes very precise frequencies of either lasers or microwaves to do that. So we can move the ion around quite violently, and that doesn't affect the internal states of the ion. Now, of course, if we're too violent, once we get to the location where we want to do the gate, we have to then cool the ion back down. Because when you do a gate between two qubits, you couple the internal degrees of freedom to those external degrees of freedom. That's how the gate's actually executed. But we have that as part of the algorithm that goes forward is once the qubits are moved to the right location, they're then cooled down to their quantum ground state and the gate is executed. So any noise that happens moving the qubits around, whether they get sort of excited or heated up, doesn't touch the internal states, the qubit states that you care about, until we turn those lasers on. And we always make sure that preparation is done beforehand to completely decouple any noise from the results there.
Great, thank you. And I think it's so interesting how you talked about the Q Sharp program getting compiled to Quasm and then the machine language, and now all of this preparation that you do to help avoid noise and just improve the quality of the system. And I'm just curious, can you talk a little bit more? You mentioned that you've developed H0 and H1 as platforms that you are able to continuously improve. Is that kind of related to what you're talking about there as to how do you actually increase the fidelity of one of these systems or add more qubits in a way that doesn't degrade the system?
That's a good question. So the traps that are in the H0 and H1 system are actually the same trap. So it's this microfabricated device with many electrodes, and the fact that one is loaded with 6 qubits right now and the other with 10 qubits is just where we started. We can put many more qubits in there, many more ions, and they can handle that traffic no problem. We have enough degrees of freedom on those electrodes, so we can add more qubits. And the nice thing about having these mobile qubits is that every time we do an interaction, we can move all the qubits that are not participating in the interaction out of the way. So although there's now more qubits in the trap, they're all sort of sitting by and watching the interactions that have to happen with the ones we've chosen. So the 2-qubit gate fidelity and all these other important metrics don't change as we add more qubits. The only thing that changes is sort of the classical control. How do we route all these qubits to the right location at the right place? And that's all sort of handled in the back end as we translate to that machine code. And it's something that as a developer, you don't have to worry a whole lot about. We just say, okay, now we can handle X number of qubits, and you can add those into your program, and away you go, knowing that they're being appropriately shuffled by our compiler. But every time we make more improvements to the classical control there, that allows us to put more qubits in and do more complex interactions.
That's really exciting. So in theory, I can start with a pretty simple program and then pretty easily just increase the number of qubits if I've parameterized it the right way.
Absolutely.
That's great. Thank you. Matt, do you have our next question? And for everyone wondering, behind the scenes, Matt Zanner, who's put a ton of effort into making this Azure Quantum Developer Workshop possible, has been primarily responsible for grabbing all of your questions and raising them up today. So a quick thank you to Matt, who's without his work, this event would not have been possible. I'm just a smiling face on your screen, but he's been doing the hard work behind the scenes. So thank you, Matt. Okay, so our next question's up here. For Stephen here at Microsoft, I saw some interest in chat about the Quantum Monte Carlo algorithm that we've made available in Azure Quantum. I was wondering if you'd be able to speak a little bit more about the algorithm at a high level and where you see it potentially being effective versus some of the other algorithms in our portfolio.
Yes, so the Quantum Monte Carlo algorithm that we're using is an example of path integral Monte Carlo. So there's essentially two main categories of Monte Carlo methods that were originally developed in the physics community for simulating quantum systems using classical computers. And these are path integral Monte Carlo and diffusion Monte Carlo methods. And this is an example of the former. And what we found is that if you take a quantum algorithm, a quantum annealing style algorithm for solving an optimization problem and simulate it using these methods that have been developed over decades by the physics community, you actually can obtain a highly effective classical optimization algorithm. So you can just forget about this, in a way, this intermediate element of simulating a physical system, just regard it directly as an optimization method. And so that's the approach we now take. If we see a place where we can alter the algorithm, which makes it a less accurate simulation of quantum physics, but a better optimizer, we'll just go for it. So that's kind of the philosophy now. And two things that make a problem suitable for these kinds of methods. First of all, if it's got a large number of variables, then that makes the problem too hard for simple methods like exhaustive search. And if the cost function landscape is a very rugged landscape with many local minima, then that means that greedy methods like gradient descent or things like that will also not be effective. So those are two criteria to look at when deciding whether to apply the methods like this one at all. As far as competing this method against some of the alternatives that we also make available in Azure Quantum, such as simulated annealing and other methods like this, it's really a very complicated question about which one is the most effective on one class of instances versus another. And in general, I'd mostly just recommend taking a very empirical kind of experimental approach to that question.
That's great. And that's kind of what Dan was talking about earlier. He suggested pick an algorithm, get a baseline, and then try some other ones. Maybe look at your landscape. And you mentioned that Quantum Monte Carlo is good for a rugged landscape or thin long barriers and stuff like that. And correct me if I'm wrong, but this is one of the algorithms in our portfolio that's able to take advantage of quantum tunneling. Is that right?
Yes, it has ultimately a process that's a classical random walk, but it mimics the behavior of quantum tunneling to escape sort of traps in the landscape, local minima that might thwart other competing algorithms.
I see. That's really interesting. Sorry, it seems I've got a bit of background noise. Matt, are you able to advance to the next question? Thank you, Stephen. Okay, next up, for Rudy at 1 qubit, who would be able to benefit from the quantum and classical engines in the Chemist Cloud, and for what kind of tasks?
Hi, everyone. So with Chemist Cloud, we're really trying to do two things right now. In the classical side, we've deployed methods so that industrial chemists working in labs or in chemical companies can use Chemist on their industrial relevant problems with classical methods. So these are just like turnkey deployments of very good, very accurate quantum chemistry algorithms targeting large problems in industry. On the quantum side, we're targeting more towards people that want to experiment with quantum computing for chemistry in any problem domain. So this is much more for the people that want to get down into the nuts and bolts of the methods and tweak really low level things to experiment. Whereas the classical side is like this can go into your industrial workflow, and like it can plug into your industrial workflow and give you very, very high quality results.
Great. So it sounds like you're really poised for impact both today, but as systems kind of scale up in the future, you're able to take advantage of those improvements and scale up your problem solving there as well.
Exactly. That's very well put. So when the time comes that we can do industry relevant solutions on quantum computers, we will already be ready, and the interfaces will be there, and our clients will be ready to make that switch like day one.
So basically, there's no disadvantage to getting started today. Even if you can't fit your whole chemistry problem on a quantum computer, getting started with optimization tools, the tools that we have available today, you're able to leverage all the work that you put into problem formulation, that sort of thing. That's really exciting, and I think for our audience today, a lot of whom have identified as developers. Personally, as a developer, I find code that I can write today is way more interesting than code that I could write a year from now. So thank you for that. Matt, do you have our next question? Okay, another one for Brian at Honeywell. How many total qubits are available in the Honeywell ion trap, and can you talk a little bit about their connectivity?
Yeah, so right now in the Honeywell system model H1, there are 10 qubits, although we expect that number to increase throughout the year as we continually upgrade our system. So 10 qubits, and they're fully connected. And so what that means is that you can program a gate between any arbitrary pair of that 10, and it should execute with the same fidelity. Right? Because our qubits are mobile, it doesn't matter which pair of qubits you want to do a gate between. We simply reshuffle the chain so everything's in the right configuration, and then execute that gate.
Right. So there's basically no disadvantage in your system to using a high-level language and being able to just assume that the fidelities are going to be what you would expect for a gate with a given number of controls. It sounds pretty straightforward. I mean,
That's
as
right.
straightforward as the subject matter gets, I suppose.
Very straightforward, just your simple high school quantum computing.
There you go. Well, this morning I couldn't have told you the difference between a Hamilton and a Hamiltonian, but I'm learning a lot today, and I hope our audience is as well. Matt, did you have the next question for us? Okay, this is one for Matt Keeson at IONQ. How long will I be waiting for my program to run on the IONQ quantum computer?
Great question. So we've been seeing average wait times of around 10 to 20 minutes these days. We're available and running jobs 24/7. That's our goal. Obviously, at times we have to upgrade the machines or perform maintenance, but all that is visible through your console. And typically, response times are less than an hour. Obviously, it does vary based on demand. If, of the few hundred people attending, if you all go submit programs, of course, they won't all run at the same time. We have to run one by one. So we use a fair queuing system, but typically, at least based on recent usage, I would expect your quantum results to return in less than 30 minutes. And of course, if you're using our simulator, which is always free, that should respond in just a matter of milliseconds or seconds.
That's exciting. And actually, it's not something that we've talked too much about today. The fact that you have a simulator, can you talk a little bit more about what that simulator is and exactly what it's simulating?
Yeah, that's a great question. So as you all have probably started to learn, if you're not already experts, in some ways, the quantum computing operations we all use are like basically linear algebra transformations. And so what's really good at doing that and simulating it for small numbers of qubits, kind of a GPU. So we used actually like GPU accelerated Fortran based simulators in the cloud, which can handle up to 29 qubits. It's a full state vector simulation. So basically it allows us to model kind of perfectly what an ideal quantum computer would do. Of course, the real computers of today that we've been talking about are all noisy, these NISQ machines. So there's interesting errors that are difficult to model classically. What makes this cool is for the computers that are available now, you can pre-flight your results for free and then run it on the real hardware and see how it behaves under real world conditions. There will, of course, come a point relatively soon, hopefully, where all of our computers and the whole ecosystem are much more powerful than anything you can run classically. But today, all of these smaller devices can be simulated, and effectively you'll get back a perfect result as if it was a error-corrected quantum computer.
That's awesome. So it's a great way to try out your program, make sure that it looks okay, and then the next step is, of course, to try it on real hardware in under 30 minutes. And that's, at least here in Montreal, that's faster than supper arrives. So that's pretty exciting.
Super exciting. And really, the extra cool thing is when you run it on the real quantum computer, you're actually firing lasers at individual atoms. So there's that cool factor you can't get with the simulator that makes it all worth it, in my opinion.
I absolutely agree. And it's a nice black box. Okay, Matt Zanner, do you have our next question? All right, this one is for Chris Grenade at Microsoft. So natively, Q# can be can Q# be implemented for all Azure backends without having to worry about transpilation or compilations between different providers? So let's say I've written a job for for Honeywell, and I'd like to run it now with IONQ, or maybe I've written it for a simulator. Is there anything that I have to worry about there, and how does that work? And Chris, you may be muted. I'm not sure if you're available to chat right now.
Yeah, thank you for the question. That's a great question. And as we've heard a bunch today so far, there's kind of two major directions you can go with Azure Quantum Service, sort of the optimization path and solvers along there, or target quantum computing. And if you're going the latter path, Q# really is a great tool to do that. It's our open source language for developing and running quantum algorithms. And with Q# and the Quantum Development Kit, we provide a number of different tools to help make that easier, including powerful editor extensions that integrate into Visual Studio Code or Visual Studio using the language server protocol. And where that connects back to this is that those editor extensions provide a lot of diagnostic information about like syntax errors, or if you call the wrong function or operation. But if you say in your Q# project file, what hardware target or simulator that you want to run your Q# program on, those same editor extensions will highlight places where you may have used functionality that's not available on that target, and you may run into issues. And so you can get that kind of feedback that helps you make that Q# program as portable as possible, or take advantage of the specific capabilities of a particular target. Moving forward, we're also investing heavily. We recently announced experiments and developmental efforts around QIR, quantum intermediate representation, to try and help make things more portable and to help bring the power of Q# to more hardware targets and bring the full power of Q# to hardware targets in that way. So there's a number of different ways that the quantum development kit is really meant to help make Q# a tool for doing exactly that, running on the different backends provided through the Azure Quantum Service.
That's really exciting. And so basically, I can use all the tools that I know and love through Visual Studio Code, or you know what? I get it. If you're not drinking the Kool-Aid on Visual Studio and you'd like to use a different editor, great. If you're in a supported editor, you're going to get feedback right while you're writing your program about whether it's going to run on your intended target. If not, if you'd like to bring your own editor, I know that there's a few Vim folks in the audience today, then you'll get that at compile time.
Yeah, and the language server protocol is, an open protocol. So if there's an editor you want to bring that kind of rich feedback to, we make the language server available for providing that as well.
Perfect, thanks. Well, that's super cool. Our next question, I believe, is for the fine folks at 1QBit. Do you have more details and experimental results regarding the DMET experiment on the H10 ring? And if you wouldn't mind just starting the question in case folks have maybe missed the earlier session, can you just summarize DMET and kind of what the context for the question's about?
This is Valentin. I can take that one, Rudy. Yeah, if you missed that earlier, so there was a small demo about a quantum chemistry experiment that we're using a method called DMET, which is a method to break your large molecule into smaller problems, essentially, and then solve these small problems instead of solving the original one. And earlier, I should quickly a notebook that takes like a ring of 10 hydrogen atoms and solve, let's say, a portion of that problem. To answer that question, yes, we have more details and experimental results, and they're actually supposed to be published really soon on arXiv. I think even maybe in the upcoming days. Actually, that's a fun timing. So if you stay tuned or if you reach out, you can definitely get a lot of information, I guess, about the method itself, and then the whole QPU experimental result we obtained using the IONQ processor.
Great, thank you. Well, I look forward to being able to read those results once they're published. Next up, I kind of wanted to switch up the format. I think we're out of our pre-written questions. I wanted to switch the format, and we've been talking today a lot about some different applications. We've seen applications for the technologies that we're talking about today from Honeywell and IONQ targeting real quantum hardware. And we've also had, our good samples from 1QBit and from, the team here at Microsoft regarding how you can use quantum-inspired optimization for, solving real-world problems today. So I'm going to kind of put my experts on the spot, and I was wondering if, at least one person from both the kind of the quantum hardware group and our quantum-inspired group could talk a little bit about, maybe an application that you're really, really excited about, either that's possible today with your technology or really soon, or maybe it's something that you've just worked on and published. But I'd love to hear a little bit more about something you're excited about. So first off, I'll ask either Matt or Sonika or Brian from IONQ or Honeywell. Is there an application that you'd be interested in sharing?
Yeah, I can share some of the applications that we've been working with various partners on at Honeywell. I think we're already seeing that there's a lot of interest in using quantum computers today to start to explore some of these optimization problems. So experiments that are going on with various logistic companies trying to figure out how to write the best algorithms to optimize whether it's packages in a container or the routing of different trucks on the road or various optimizations in supply chain. I think we're seeing that there's a lot of interest today in running these optimization programs on today's quantum hardware. Now, I will say you're not solving anything that you can't solve on a classical computer yet, but developing these techniques and optimizing these algorithms today to prepare for larger qubit numbers and higher fidelities, which will enable problems that are difficult to solve otherwise, is something we're already seeing today, and I think is quite exciting.
It is, and as you were saying earlier, you're already investing in increasing the capabilities of your hardware. And through Azure Quantum, it's going to be pretty straightforward to take advantage of those improvements. So if you get started today, there's no better time to start exploring your problem domain than when that's available. You can make best use of it. Now, I also saw some folks from IONQ come off mute. Did you have a case that you wanted to add?
Yeah, thanks, Mike. Yeah, so you were asking about an application that we've run recently that we're excited about, and I wanted to mention, so recently we've had some pretty exciting results in quantum machine learning. Our 11-qubit trapped ion system was recently used to do both image recognition and image generation. And in both cases, in the image recognition case, the performance was equivalent to that of the classical computer performance. And in the image generation case, we actually outperformed a purely classical system. This is very, very exciting. This is very, very exciting because when our next generation systems come online, in the field of quantum machine learning, we already expect to start getting competitive with classical computers.
Well, those are some really exciting results. Thank you. And I suppose if you have a link to anything that you've published or written about, feel free to post those in the Q&A, and we can help amplify if anyone's interested. Now, next, I wanted to move that same question to the folks at 1QBit, and also Stephen. I'm sure you probably have an application top of mind, but would you mind sharing just briefly some of the applications for your technologies in the kind of the quantum-inspired domain? And I know that at 1QBit you've been working on some, I'll tentatively call them hybrid approaches. But yeah, would you mind sharing some use cases there as well?
This is Valentin. I think it's a bit hard for us to capture the full scope because we only really focusing on the quantum chemistry side of things at 1QBit. We have a whole division dedicated to applications of machine learning in fields as diverse as health, or we've done some quantum computing in finances as well. We've been also looking at the optimization. So it's really hard, I think, to summarize this question. I think overall, when people usually present 1QBit and the number of topics we've been looking into in various capacity, we probably have like, I don't know, 10 different fields that, again, go from optimization to various fields of science. So that's a bit complicated, I guess, to get into at the moment.
No, but that's really interesting, because one of the things that I noticed is as we went through our session today, I was seeing a ton of questions about, can I apply this to this problem that I'm working on or my domain? And it seems like the answer is, probably yes. Now, it may not be straightforward, and impact, is difficult to quantify right now depending on the problem. But there's so many different problem domains that can benefit from these technologies. And so it's very likely that everyone in the audience here likely has a problem that can be solved, although certainly not every problem can be.
I think this is very exciting because, like many people said, we are at very experimental stages right now. We're not quite sure of all the possibilities quantum computers have to offer, and we're just piling up on innovation, both on the algorithmic side and also in the hardware advances, which means that this is the perfect time to try to wonder about this kind of question, like, can this technology do anything for me? Can I borrow ideas from various fields and try to be one of the main innovators in my field and make a breakthrough in that? I think these are great questions to have right now, and that people should definitely talk with actors in quantum computing to try to see what may be an opportunity.
That's great, thank you. And lastly, I wanted to ask Stephen. I know you have the kind of enviable job of working with a lot of the companies that we heard about during the break. But is there an application of what you're working on in the quantum-inspired domain that you're kind of particularly interested or inspired by right now?
Yes, well, there's the interesting thing about optimization problems is that you really find them across every sector that you can think of, whether it's aerospace or biomedical or logistics or basically you name it. Everybody has optimization problems. So it's been very interesting to learn about all these different industries. One area that I especially find compelling is the healthcare space, because it's kind of very very visceral to think about actual patients with problems and trying to help them. So one of the projects that I was especially involved with was a project of using optimization algorithms to do automated design of pulse sequences for MRI machines so that they can do their scans more quickly. And so then it really brings it down to something you can relate to. Nobody likes sitting in those noisy, claustrophobic machines, and if you could sit there for 10 minutes instead of 40 minutes, the benefit of that is very obvious. Some of the other things also can have big benefits, say in the finance industry or something, but it's much more abstract. And so I kind of like these really relatable ones.
Yeah, absolutely. And of course, worldwide, healthcare has been top of mind. And so, there's a ton of optimization problems there. There's a ton of chemistry problems there. So I really love seeing the impact that these solutions have been able to have already. And we're only just getting into public preview. That's the most exciting thing is, Satya, our CEO, has talked a lot about momentum in the industry. And I think we're at a point where the momentum is just increasing, and with that, the impact and really driving, not just improvements to a lot of businesses, to a lot of people, but general improvements to people's lives. And that's really exciting for me. Next up, I believe we have a one last question for Chris on our team. How can I use Q# alongside existing classical languages like Python?
Thank you. That's a great question. So I personally find it easiest to think of it, if I think of Q# as kind of being an accelerator, the same way I might think of writing something in CUDA if I want to target a GPU, I can write a program in Q# and then call it from an existing conventional language like Python. And we have a number of different samples of how to do that over in our samples. So let me go take a look at that. So if I come over here to Visual Studio Code running some of the samples provided with a quantum development kit, one of the examples we have uses Python to run a kind of quantum experiment called the CHSH game. When I scroll down here a little bit, I see this play quantum strategy.simulate call. And what that's actually doing is it's imported from my Q# code, that quantum operation, defined here as an entry point that gets to use that I ask for qubits and I go and do something with those qubits. And then it dispatches that Q# program over to the simulator so that when I run it from Python, it uses Python and Q# together to run that application. Takes just a moment, then you should see. And that same idea works if I'm submitting Q# programs to the Azure Quantum Service. The Q#.Azure package allows me to take those same Q# operations and send them over to the Azure Quantum Service. So here, for instance, if I want to sample some random numbers, I can do so in the same way, switch over to that, and this will run this Q# operation both locally on my simulator and here also submit it over to the Azure Quantum Service using the Q#.Azure.execute function. So it makes it really easy to run that whole test locally, then deploy to the service sort of pipeline you heard about earlier, integrating Q# and Python together to make a bigger application like that. There's lots more samples that you can see in our documentation and in the samples browser at docs.microsoft.com/samples.
That's really interesting. Thank you. And that's very similar to what Sonika and Matt showed earlier as well with their machine learning examples. So very cool to see that interoperability. And it's great because if you already have some code in Python that you've been using or you've been thinking about, it's a really quick and easy way to get started using Q# and Azure Quantum. So that's really great to see. Next up, I think we're about out of time for questions. So I wanted to go ahead and share some of the resources that we've been talking about today. Of course, we've covered a lot of ground, so there's a lot to talk about. The first ones that I wanted to call out are some of our really great learning materials, starting with MS Learn. Now, if you don't know, MS Learn is Microsoft's online learning platform, and it's a free, openly accessible, self-paced learning solution, and it's interactive as well. So it will help you learn everything about the fundamentals of quantum computing, about Azure Quantum, and about optimization. So I highly recommend that. We have many hours of content, and it's a wonderful experience. The teams put so much effort in. It's a great place to start. And if you're looking to get started specifically with Q#, really build up your quantum programming chops, we have this excellent resource called the Quantum Katas. Now, when I was a kid, I learned karate, and that was one of the ways that we developed skills and turned them into reflexes, is we learned katas with different moves, and it's the exact same idea but applied to quantum computing and quantum programming. So you'll start out by learning some basics, applying them, and slowly building up your skills until you're able to express full algorithms. So that's a really great resource as well. Now, we've talked a lot about the Q# community, but we wouldn't be here if it wasn't for them. So if you'd like to go ahead and get started, you can go to qsharp.community. That is actually a link, and get started, get plugged in there. And of course, we can't talk about Q# without talking about our quantum development kit. That's available at aka.ms/get-started-qdk. And the QDK is, of course, open source, as are most of our tools. So if you'd like to become a contributor to the QDK, check out that next link, aka.ms/contribute-qdk. Now, we're all here to talk about Azure Quantum, and if you're sitting there rearing to go to aka.ms/aqpreview. That's going to bring you right to the Azure portal. And if you don't already have an Azure subscription, that's the place to sign up, get one, and get started. Lastly, I'll point you to the Q# blog to stay up to date on the latest developments with Q#, and the Microsoft Quantum blog to stay up to date with the latest developments for everything that we're doing here at Microsoft related to quantum. So thank you so much for joining. It's been an absolute pleasure to have you. And before I end, I just wanted to take a moment and thank our wonderful panel of experts who have worked so hard to prepare the content that they shared with you today. It wouldn't have been possible without you. So thank you so much. I'd also like to thank all of the engineering teams at our partners, OneQubit, Honeywell, and IONQ, who've been working tirelessly to integrate with Azure Quantum and make all of this possible. And of course, we have 2 other Azure Quantum partners that we're still working with getting them out. I'm very excited to welcome Toshiba and QCI once their solutions are publicly available in Azure Quantum. And lastly, all of this would be for naught if it wasn't for you. Now at Microsoft, our mission is to empower every person and organization on the planet to achieve more. And I hope that we've helped you today. And from everyone here on the Azure Quantum team and on behalf of our partners, we can't wait to hear what you'll do and build with Azure Quantum. Thank you so much.
Thank you everyone for joining us today. You can access the event recording at the same location used to join today. Please take a moment to respond to a short survey specific to today's workshop. You will also find a link to access a completion certificate. Click on the messages button and you'll find both links there. I'd like to extend a thank you to all of our presenters. This concludes today's event. You may now disconnect.